Imagine a giant spaceship the size of an entire city flying through space. Around it, thousands and thousands of space rocks floating in every direction, some small like cars, others huge like mountains. Sounds simple, right? You just need to dodge the rocks and keep going forward. But the truth is much more complicated than the movies show. The space between asteroids isn't like an obstacle course where you see everything clearly. These rocks move at insane speeds, spin in unpredictable ways, and worst of all, some are so dark you can barely see them until you're dangerously close. And if you're piloting a massive ship like the one in the image, every movement needs to be calculated hours in advance, because a machine this gigantic can't simply turn quickly like a car. Get ready for a relaxing journey as we explore the real secrets and dangers of navigating through an asteroid field. Subscribe to the channel. Leave your like and comment from which part of the world you're watching. Get comfortable and relax. Let's begin. Have you ever wondered if Han Solo's daring flight through an asteroid field in Star Wars was realistic? Most of us have grown up watching science fiction movies where spaceships zip and dodge through dense fields of tumbling space rocks, narrowly avoiding collisions at every turn. These thrilling scenes have shaped our perception of what asteroid fields must be like. But the truth is far different from what Hollywood has led us to believe. In reality, asteroid fields and belts are incredibly sparse places. The main asteroid belt between Mars and Jupiter, which contains millions of asteroids, spreads these objects across such an enormous volume that the average distance between sizable asteroids is hundreds of thousands of kilometers. To put this in perspective, if you were standing on an asteroid in our solar system's asteroid belt, you would likely not be able to see any other asteroids with the naked eye. They would be too far away, appearing as mere points of light similar to stars, if visible at all. This vast emptiness is a far cry from the densely packed obstacle courses portrayed in movies, where asteroids seem to be separated by mere meters. Film directors choose this unrealistic portrayal for obvious reasons. A scene where a spacecraft flies through empty space for hours without encountering anything would make for rather boring cinema. The dramatic tension created by navigating through a dense field of deadly obstacles is simply too good to pass up, even if it means sacrificing scientific accuracy. The misrepresentation goes beyond just density. Movies typically show asteroids moving chaotically, tumbling and spinning in random directions. While asteroids do rotate and have some relative motion to each other, in our solar system they generally follow predictable orbital paths around the Sun. They aren't randomly bouncing off each other like billiard balls. In fact, collisions between asteroids are relatively rare events, occurring on timescales of millions of years. Despite this sparsity, navigation through real asteroid regions is still challenging, just for different reasons than movies suggest. The true challenge lies in detecting small objects from great distances while travelling at extremely high velocities. Even a pebble-sized rock can cause catastrophic damage to a spacecraft when relative speeds reach tens of thousands of kilometers per hour. It's like trying to spot a bullet coming at you from kilometers away. The danger isn't in the number of bullets, but in the devastating impact of just one. Space agencies like NASA and ESA take these threats very seriously, carefully plotting trajectories that minimize risk when sending probes through asteroid-rich regions. When the New Horizons spacecraft travelled through the Kuiper Belt beyond Neptune, mission planners spent years calculating a path that would avoid potential collisions, despite the extremely low probability of encountering anything at all. The mathematical reality of space travel also contributes to the misconception. The sheer scale of space is difficult for human minds to comprehend. We're accustomed to thinking in terms of terrestrial distances and speeds. The vastness of space operates on a different order of magnitude entirely. The entire International Space Station, for example, could easily navigate through the asteroid belt without any special evasive maneuvers and face virtually no risk of collision. Another aspect that science fiction often overlooks is the three-dimensional nature of space. Movies typically portray asteroid fields as flat, two-dimensional regions, when in reality, they extend in all directions. This further reduces the probability of collision, as objects aren't confined to a single plane but are distributed throughout a much larger volume of space. For spacecraft designers and mission planners, the real concerns about asteroid navigation have more to do with precision tracking and detection capabilities than with split-second piloting reflexes. Modern spacecraft carry sophisticated sensors designed to detect objects at great distances, giving controllers ample time to calculate and implement course corrections when necessary. This isn't to say that dense collections of space debris don't exist. Following catastrophic collisions between asteroids, temporary debris fields can form with higher densities. Similarly, planetary ring systems like those around Saturn contain countless particles but are still far less dense than movie portrayals suggest. Even in these relatively denser regions, spacecraft like Cassini have successfully navigated for years without impacts from significant objects. The persistent myth of densely packed asteroid fields has practical consequences beyond mere scientific inaccuracy. It affects public perception of space exploration challenges and risks. When engineers and scientists try to communicate the actual technical difficulties of navigating in space, they must first overcome these deeply ingrained misconceptions. The real challenges of asteroid field navigation include precise trajectory calculations, developing sensitive detection equipment that can function reliably in the harsh environment of space, and creating spacecraft with enough durability to withstand impacts from micrometeoroids, tiny dust particles that are the most common impact threat. Space agencies and private companies are continually improving technologies to address these challenges. Advanced radar systems, optical telescopes, and laser ranging equipment are being developed to detect smaller objects at greater distances. New materials and shield designs help protect vital spacecraft components from micrometeoroid impacts, and increasingly sophisticated computer models help predict the movement of known objects and calculate probabilities of encountering unknown ones. So the next time you watch a spaceship darting through a field of closely packed asteroids, remember that while it makes for exciting cinema, it bears little resemblance to the vast, mostly empty reality of space. The true story of how we navigate these regions may lack the immediate visual drama of science fiction, but it represents a no less impressive triumph of human ingenuity and technological advancement. Relative velocities and the challenge of spatial navigation. Think about catching a baseball thrown at 20 miles per hour, challenging but manageable. Now imagine trying to catch a bullet fired from a gun. That impossible comparison begins to illustrate the problem of relative velocity in space, one of the most underappreciated challenges in navigating asteroid fields and other space environments. In space, objects move at speeds that are difficult for our earthbound minds to comprehend. The average asteroid in the main belt orbits the Sun at approximately 20 kilometers per second, while spacecraft often travel even faster. When two objects approach each other in space, their velocities combine to create relative speeds that can reach tens or even hundreds of kilometers per second. At these velocities, collision avoidance becomes a matter of advanced prediction rather than real-time reaction, even if a spacecraft detected an asteroid 1,000 kilometers away. At a relative approach speed of 20 kilometers per second, the vessel would have just 50 seconds before impact. This time frame shrinks dramatically when considering smaller objects that can only be detected at closer ranges. The physics is unforgiving. By the time an object becomes visible or detectable, it might already be too late to avoid it. This reality creates a paradox for navigation systems. The faster a spacecraft travels, the more ground it can cover and the less time a mission takes. Yet those higher speeds exponentially increase collision risks and decrease reaction times. Every increase in velocity creates a corresponding decrease in the window available for detection and evasive action. Current propulsion systems compound this challenge. Chemical rockets, still the most common form of spacecraft propulsion, provide powerful but brief acceleration once a spacecraft reaches its cruising velocity. Making significant course changes requires substantial fuel reserves. Ion engines and other advanced propulsion systems offer better efficiency but generate less immediate thrust, making them less suitable for last-minute evasive maneuvers. The three-dimensional nature of space adds another layer of complexity. On Earth, vehicles primarily navigate in two dimensions, moving across a relatively flat surface. Even aircraft, while operating in three dimensions, are constrained by gravity and atmospheric effects. In space, objects approach from any direction with equal probability, requiring detection systems with complete spherical coverage and navigation systems capable of executing maneuvers in any direction. Orbital mechanics further complicates matters. Unlike cars or aircraft, spacecraft and asteroids don't move in straight lines. They follow curved orbital paths dictated by gravitational influences from the Sun, planets, and other massive objects. Predicting these trajectories requires complex mathematical models that account for numerous gravitational interactions. Even small errors in these calculations can lead to significant position discrepancies over time, potentially turning what was calculated as a safe trajectory into a collision course. The challenge of relative velocity isn't limited to large asteroids. Space contains countless smaller objects, from centimetre-sized rocks to microscopic dust particles. At extreme relative velocities, even these tiny objects carry enormous kinetic energy. A centimetre-sized rock moving at 20 kilometers per second relative to a spacecraft carries the kinetic energy of a hand grenade. Even dust particles, too small to detect before impact, can gradually erode spacecraft surfaces and damage sensitive equipment over time. Current detection technologies struggle with these realities. Optical systems rely on reflected sunlight, making dark or small objects difficult to spot until they're dangerously close. Radar systems offer better detection of nearby objects, regardless of their reflectivity, but have limited range in the vastness of space. Both systems face fundamental physical constraints that engineering improvements can mitigate but never entirely overcome. Time delay presents another critical challenge. Electronic systems require time to process sensor data, calculate trajectories, determine collision risks, and implement avoidance maneuvers, even with the fastest computers. This processing chain introduces delays measured in seconds, precious time when objects are approaching at hypervelocity. This creates a minimum detection distance required for avoidance, regardless of how sensitive the detection equipment might be. For human pilots, these challenges become nearly insurmountable. The human brain evolved to track objects moving at speeds encountered in nature, animals running, projectiles thrown by hand, even modern vehicles. It simply cannot process and react to objects moving at orbital velocities. This is why automated systems are essential for space navigation, particularly in potentially hazardous regions. The development of effective navigation systems for asteroid environments requires balancing multiple competing priorities. Detection systems must be sensitive enough to spot distant objects, yet robust enough to filter out false positives. Avoidance algorithms must be sophisticated enough to calculate optimal evasion strategies, yet simple enough to execute quickly. Propulsion systems must be powerful enough for effective evasion, yet efficient enough for long-duration missions. Some promising technologies are emerging to address these challenges. Artificial intelligence systems can process sensor data and implement avoidance maneuvers far more quickly than traditional computing approaches. Distributed sensor networks, with multiple spacecraft sharing detection data, can provide earlier warnings and more accurate trajectory predictions. Advanced materials science is creating more resilient spacecraft components that can better withstand impacts from smaller particles. For future missions venturing deeper into asteroid-rich environments, such as long-term exploration of the main belt or mining operations on resource-rich asteroids, these navigation challenges will become increasingly significant. Mission planners must constantly balance risk against reward, calculating acceptable probabilities of collision against mission objectives. Ultimately, the problem of relative velocity in space navigation isn't something that can be solved completely. It can only be managed through increasingly sophisticated technology and careful mission planning. As our understanding of asteroid distributions improves and our detection and avoidance systems become more advanced, we can push the boundaries of safe navigation further. But we can never eliminate the fundamental challenge posed by objects moving at speeds that defy human intuition. The vast emptiness of space provides some margin for error, but the consequences of miscalculation remain catastrophic. This reality shapes every aspect of spacecraft design and mission planning, creating a constant tension between the desire to explore and the need to preserve expensive, often irreplaceable spacecraft and, when applicable, the lives of any human crew members aboard. The profound challenges of relative velocity in space navigation are made even more complex by another critical factor: the actual distribution patterns of asteroids throughout our solar system. Far from being uniformly scattered, asteroids form distinct populations with unique characteristics that directly impact navigation strategies and risk assessments. The most famous concentration of asteroids is the main asteroid belt, located between the orbits of Mars and Jupiter. This region houses millions of asteroids, from the massive dwarf planet Ceres at nearly 1,000 kilometers in diameter down to countless objects too small to detect from Earth. What makes this region particularly interesting is that it's not a chaotic jumble as often portrayed, but rather a structured collection of objects in well-defined orbits around the Sun. Within the main belt, asteroids aren't distributed evenly. They form distinct bands called Kirkwood gaps where asteroids are notably absent. These gaps result from orbital resonances with Jupiter, where the giant planet's gravitational influence has effectively cleared these regions over billions of years. Understanding these structured distribution patterns is crucial for mission planning, as these relatively empty corridors provide safer passages for spacecraft traversing the belt. The main belt isn't the only significant asteroid population in our solar system. Beyond the orbit of Neptune lies the Kuiper belt, home to icy bodies that represent a transition between rocky asteroids and comets. This region extends from about 30 astronomical units, the distance from Earth to the Sun, to 50 astronomical units, and is estimated to contain hundreds of thousands of objects larger than 100 kilometers in diameter, along with trillions of smaller bodies. Closer to Earth, we encounter the near-Earth asteroids, or NEAs. These objects have orbits that bring them into the inner solar system, sometimes crossing Earth's path. While representing a smaller population, currently we've catalogued about 25,000 NEAs larger than 140 meters. They pose proportionally greater navigational concerns due to their proximity to Earth-based missions. Their orbits are often more eccentric and less predictable, having been altered by close planetary encounters. Another fascinating asteroid population consists of the Trojan asteroids, which share orbits with planets while maintaining stable positions. Jupiter's Trojans are the most numerous, with more than 7,000 known objects clustered at the Lagrange point 60 degrees ahead of and behind Jupiter in its orbit. Neptune, Mars, and even Earth have smaller Trojan populations as well. These regions represent unique navigational environments where objects maintain relatively stable positions with respect to their host planets. The three-dimensional distribution of asteroids adds another layer of complexity often overlooked. While often depicted as flat rings or belts, asteroid populations extend above and below the ecliptic plane, the flat plane that roughly corresponds to the orbits of the planets. Some asteroids have highly inclined orbits, reaching far above or below this reference plane. The inclination distribution varies between different asteroid groups, with some populations showing greater vertical dispersion than others. Asteroid distribution is also affected by composition. Scientists classify asteroids into different types based on their spectral characteristics, which indicate different material compositions. These types aren't randomly distributed, but show distinct patterns. For instance, S-type, stony asteroids dominate the inner regions of the main belt, while C-type carbonaceous asteroids become more common in the outer regions. This compositional distribution affects not just scientific interest, but also practical concerns like visibility for detection systems, as different materials reflect light differently. Family groups represent another important aspect of asteroid distribution. These are clusters of asteroids believed to have originated from the fragmentation of a larger parent body. The Vesta family, Coronis family, and Themis family are notable examples. These families share similar orbital characteristics and compositions, effectively creating higher density regions within the broader belt. From a navigation perspective, encountering one member of a family might indicate an elevated risk of encountering others nearby. Dynamic processes continually reshape asteroid distributions. Jupiter's massive gravitational influence can gradually alter asteroid orbits over millions of years. Collisions between asteroids, while rare on human timescales, create both new fragments and subtle changes in trajectories. The Yarkovsky effect, a force resulting from uneven heating and cooling of an asteroid's surface, can gradually modify the orbits of smaller asteroids over time. These dynamic changes mean that asteroid distribution maps require regular updating, especially for long-duration mission planning. The Yorp effect, Yarkovsky-O'Keefe-Radzievsky-Paddock effect, further complicates matters by altering asteroid rotation rates and axis orientations over time. As rotation patterns change, so too can an asteroid's trajectory, adding another level of unpredictability to long-term distribution forecasts. Understanding these complex distribution patterns requires extensive observation programs. Ground-based surveys like Pan-STARRS and the Catalina Sky Survey have dramatically increased our catalogue of known asteroids. Space-based observatories like NEOWISE provide complementary data, particularly on asteroid sizes and compositions. However, our knowledge remains incomplete, especially regarding smaller objects and those in the outer solar system. For spacecraft navigation, this detailed understanding of asteroid distribution translates directly into risk assessment. Missions can be timed and trajectories plotted to avoid known regions of higher density. The structured nature of the main belt, with its Kirkwood gaps and family clusters, allows for strategic planning that wasn't possible in earlier eras of space exploration. Despite the enormous numbers involved, millions of asteroids in the main belt alone, the vast volume of space means that deliberate visits to asteroids require precise targeting rather than random encounters. When spacecraft like Dawn visited Vesta and Ceres, or when OSIR-ISR-EX rendezvoused with Bennu, these meetings were the result of careful planning, not chance encounters while passing through densely populated regions. For future exploration and potential commercial activities like asteroid mining, this detailed mapping of distribution patterns will become increasingly valuable. Resources aren't evenly distributed throughout asteroid populations, and understanding which regions are rich in particular materials could guide exploration strategies. Similarly, understanding distribution patterns aids in identifying potentially hazardous asteroids that might pose future threats to Earth. The study of asteroid distribution continues to evolve as our observational capabilities improve. Each new survey discovers previously unknown objects and refines our understanding of population patterns. This growing knowledge base forms the foundation for increasingly sophisticated navigation strategies as humanity pushes further into the asteroid frontier. While navigating the complex distribution of asteroids throughout our solar system presents significant challenges, equally crucial are the limitations of our detection and tracking systems. These technological constraints directly impact our ability to safely navigate spacecraft through asteroid environments, regardless of how well we understand their general distribution patterns. Current detection systems rely primarily on optical telescopes that detect sunlight reflected off an asteroid's surface. This approach, while proven, has fundamental limitations. First and foremost is the issue of albedo, an object's reflectivity. Many asteroids are extremely dark, reflecting as little as 3 to 4% of the sunlight that hits them. These low albedo objects are inherently difficult to detect against the black background of space, effectively remaining invisible until they're dangerously close. Size creates another critical threshold. With current ground-based technology, we can reliably detect objects larger than about 100 meters in near-Earth space, but smaller asteroids often escape detection until they're much closer. Yet even a 10-meter asteroid could cause catastrophic damage to a spacecraft. This creates a troubling blind spot where objects large enough to destroy a mission but too small for early detection pose an ongoing navigational threat. Distance compounds these challenges. The brightness of a reflected object decreases with the square of its distance, meaning that an asteroid twice as far away appears only 1/4 as bright. For distant regions like the Kuiper Belt, only the largest objects are detectable from Earth, leaving vast populations of smaller bodies effectively invisible to our current survey techniques. Optical detection also faces a geometric limitation known as phase angle. Asteroids are most visible when fully illuminated from our perspective, similar to how a full moon appears brighter than a crescent. Objects located in directions close to the Sun, including those approaching Earth from that direction, are particularly difficult to spot because they present minimal illuminated surface area to observers. This creates dangerous blind spots in our detection coverage. Radar offers a powerful complement to optical detection for near-Earth objects, as it doesn't rely on reflected sunlight. Systems like NASA's Goldstone Solar System Radar and the Arecibo Observatory, before its collapse in 2020, could provide detailed information about an asteroid's size, shape, dot, and surface features. However, radar's effectiveness decreases dramatically with distance, limiting its utility to objects that come relatively close to Earth, typically within 0.1 astronomical units. For spacecraft navigating through asteroid regions, onboard detection systems face even greater constraints. Mass and power limitations restrict the size and capability of sensors that can be deployed on a spacecraft. While a ground-based telescope might have a mirror measuring meters in diameter, a spacecraft-based detection system must function with much smaller apertures, drastically reducing its ability to spot distant objects. Processing power creates another bottleneck. The computational demands of real-time image analysis to identify approaching objects, calculate their trajectories, and determine collision risks are substantial. Spacecraft computers, which must be radiation-hardened and highly reliable, typically lag years behind commercial computing capabilities. This processing limitation directly impacts how quickly a spacecraft can identify and respond to potential hazards. Field of view presents a particular challenge for spacecraft-based detection. While ground-based surveys can systematically scan large portions of the sky, a spacecraft's sensors typically have a much narrower field of view. This creates a trade-off. Wide-field sensors might provide better overall coverage, but sacrifice the ability to detect smaller or more distant objects, while narrow-field sensors offer better detection capability, but might miss objects approaching from unexpected directions. The thermal environment of space introduces additional complications. Infrared detection systems, which can identify asteroids based on their heat signatures rather than reflected light, must contend with solar heating of spacecraft components. This creates background noise that can mask the subtle thermal signatures of distant asteroids. Cooling systems can mitigate this issue but add mass, complexity, and power demands to the spacecraft. For tracking already discovered asteroids, we face the challenge of maintaining an accurate catalogue of orbital elements. Each asteroid's orbit is influenced by numerous factors, including the gravitational pulls of planets and other large bodies, solar radiation pressure, and potential outgassing for comet-like objects. Without regular observations to refine orbital calculations, prediction accuracy degrades over time, potentially turning a supposedly safe trajectory into a collision course. Data sharing between different observation platforms represents both a technical and organizational challenge. Observations from multiple sources must be correctly correlated to build comprehensive tracking data. This requires sophisticated software systems and cooperative protocols between different space agencies, observatories, and now increasingly, private space companies. The tracking problem scales exponentially with the number of objects being monitored. Our current catalogue includes over 1 million asteroids with well-defined orbits, but this represents only a fraction of the total population. As detection capabilities improve and more objects are discovered, the computational and organizational demands of tracking them all grows accordingly. False positives and data artifacts create additional complications. Cosmic rays striking detection sensors, satellite streaks across telescope images, and other phenomena can mimic the signatures of asteroids. Filtering out these false detections requires sophisticated algorithms and often human verification, adding time delays to the detection process. For spacecraft missions, these detection and tracking limitations translate directly into navigational uncertainty. Mission planners must build in safety margins and contingency protocols to account for the possibility of undetected objects. These precautions often include redundant systems, enhanced shielding on critical components, and trajectory plans that minimize time spent in higher-risk regions. Addressing these limitations requires a multifaceted approach. Next-generation ground-based systems like the Vera-CA or Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, promise to dramatically increase our detection capabilities for near-Earth objects. Space-based observatories dedicated to asteroid detection could overcome many of the limitations faced by ground-based systems, particularly the constraints imposed by Earth's atmosphere and the inability to observe regions close to the Sun. For spacecraft, advances in miniaturized sensors, more powerful radiation-hardened processors, and improved detection algorithms offer paths toward better onboard detection capabilities. Distributed detection networks, where multiple spacecraft share detection data, could provide more comprehensive coverage than any single vessel could achieve alone. Despite these promising developments, the fundamental physics of detection, involving light, distance, and object size, means that perfect detection remains impossible. There will always be objects too small, too dark, or approaching from unfortunate angles to detect before they pose a threat. This reality shapes every aspect of deep space mission planning and reinforces the need for robust spacecraft designs that can withstand the occasional impact from smaller particles that inevitably will go undetected. Beyond the inherent challenges of detecting and tracking asteroids, another formidable obstacle to safe navigation comes from an unexpected direction: the Sun itself. Our star, the ultimate source of energy for our solar system, creates numerous complications for spacecraft attempting to navigate through asteroid environments. Solar radiation impacts navigation operations in multiple, often subtle ways that compound the already significant challenges of space travel. Perhaps most directly, intense sunlight interferes with the optical systems spacecraft rely on to detect potential hazards. When a spacecraft is positioned with the Sun in or near its field of view, the overwhelming brightness creates what engineers call a sun exclusion zone, a cone-shaped region where optical sensors are essentially blinded. This creates a serious vulnerability in spacecraft detection systems. Asteroids approaching from directions near the Sun become nearly impossible to spot using conventional optical methods. This isn't merely a theoretical concern. Several near-Earth asteroids have been discovered only after they passed Earth, having approached from the direction of the Sun and remaining effectively invisible until they had already moved past our planet. Solar flares and coronal mass ejections represent another class of solar-induced navigation hazards. These violent eruptions send streams of high-energy particles racing through the solar system at speeds approaching that of light. When these particle storms hit a spacecraft, they can temporarily disrupt or permanently damage sensitive electronic systems, including the very navigation computers responsible for hazard avoidance. Modern spacecraft incorporate radiation-hardened components designed to withstand these events, but complete immunity is impossible. particularly powerful solar storms can overwhelm even hardened systems, potentially leaving a spacecraft temporarily blinded, disoriented, or unable to execute avoidance maneuvers precisely when it might need these capabilities most. The radiation environment created by the Sun also causes gradual degradation of spacecraft systems over time. Solar radiation slowly damages solar panels, reducing power generation capacity throughout a mission's duration, since detection systems and propulsion both require power. This degradation directly impacts a spacecraft's ability to navigate safely as a mission progresses. Optical sensors suffer as well, with lenses and detectors experiencing reduced sensitivity after prolonged radiation exposure. Beyond these direct effects on spacecraft systems, solar radiation also influences the very asteroids a mission might be trying to navigate among. The Yarkovsky effect, mentioned earlier, results from uneven heating of an asteroid's surface by the Sun. As the asteroid rotates, the heated portion radiates thermal energy back into space, creating a tiny but persistent thrust that, over time, can significantly alter the object's orbit. For small asteroids less than 1 kilometer in diameter, this effect can shift orbits enough to make long-term trajectory predictions unreliable. A spacecraft might plot a course through what current observations suggest is a safe corridor, only to find that solar-induced orbital drift has placed previously distant asteroids directly in its path. A related phenomenon, the YORP effect, causes solar radiation to gradually alter an asteroid's rotation rate and axis orientation. As rotation patterns change, so too can the Yarkovsky effect, creating complex, difficult-to-model changes in trajectory. For navigation planning, these solar-induced orbital uncertainties require additional safety margins, further constraining potential routes. Solar radiation pressure directly affects spacecraft trajectories as well. Photons from the Sun, though massless, carry momentum that exerts a small but continuous force on spacecraft surfaces. For large, lightweight structures like solar panels, this pressure creates a noticeable acceleration over time. Navigation systems must constantly account for this effect to maintain accurate positional awareness. The interaction between solar radiation and spacecraft surfaces isn't uniform but depends on material properties, surface orientation, and the spacecraft's changing position relative to the Sun. This makes solar pressure effects difficult to model precisely, introducing another source of navigational uncertainty that compounds over time and distance. Temperature fluctuations caused by changing solar exposure create additional complications. As spacecraft components heat and cool, they expand and contract slightly, potentially altering the precise alignment of sensors and thrusters. For navigation systems that might need to detect distant objects or execute precise burns, even tiny misalignments can have significant consequences. Protecting against solar radiation effects requires adding mass in the form of shielding, radiation-hardened components, and redundant systems. This additional mass directly impacts a spacecraft's maneuverability, creating a trade-off between protection and agility. Heavier spacecraft require more fuel for course corrections and have slower response times, potentially limiting their ability to avoid detected hazards. Solar cycles add yet another layer of complexity to navigation planning. The Sun follows roughly 11-year cycles of activity, with periods of relative calm interrupted by phases of intense solar flares and ejections. Missions travelling through asteroid regions during solar maxima face greater risks from radiation effects than those travelling during quieter periods. This cyclical pattern must be factored into mission timing when possible. For missions venturing to the outer solar system, the diminishing solar intensity creates different challenges. Detection systems designed to operate in the bright environment near Earth must function with significantly less available light. Power generation from solar panels becomes less efficient, constraining the energy available for navigation systems. This is particularly relevant for missions to the Kuiper Belt and other distant asteroid populations. The solutions to these solar-related navigation challenges are as varied as the problems themselves. Advanced filter systems can help optical sensors function even when pointing near the sun. Multispectral detection approaches can partially overcome the limitations of visible light systems. Improved modelling of solar effects on both spacecraft and asteroids can reduce navigational uncertainty. Some missions have even turned solar radiation from a hindrance into a help, using solar sails that intentionally harness radiation pressure for propulsion. These lightweight structures offer the potential for fuel-free navigation, though their slow acceleration limits their usefulness for rapid avoidance maneuvers. As our exploration pushes further into asteroid-rich environments, developing more robust solutions to solar radiation challenges will be essential. Future spacecraft will likely incorporate even more sophisticated radiation protection, detection systems that function across wider spectral ranges, and navigation algorithms that better account for solar-induced uncertainties in both spacecraft and asteroid trajectories. The Sun's influence on space navigation serves as a powerful reminder of how interconnected the challenges of space exploration truly are. What seems at first like a simple problem of spotting and avoiding physical objects becomes, on closer examination, a complex interplay of radiation physics, materials science, orbital mechanics, and electronic engineering. While solar radiation presents significant challenges to asteroid field navigation, communication delay introduces an equally fundamental obstacle that reshapes how we must approach the entire concept of space navigation. The vast distances involved in space exploration impose unavoidable time lags in communications that make Earth-based control of spacecraft navigating through hazardous regions effectively impossible. This delay stems from a simple but immutable fact: radio signals, travelling at the speed of light, take measurable time to cross the enormous distances of space, even at the incredible speed of approximately 300,000 kilometers per second. A signal from Earth to a spacecraft near Mars takes anywhere from 4 to 24 minutes to arrive, depending on the relative positions of the two planets in their orbits. This means that if a spacecraft near Mars detects an asteroid on a collision course, the information about this threat would take minutes to reach Earth. Mission controllers would then need additional time to assess the situation and determine an appropriate response. Their instructions would then take another several minutes to reach the spacecraft. By the time the evasive maneuver commands arrived, the collision would have already occurred or been avoided by automated systems. The problem compounds dramatically as missions venture deeper into the solar system. For a spacecraft in the main asteroid belt, communications can take 30 to 50 minutes each way. At Neptune's distance, the delay extends to about 4 hours each way. These times represent absolute minimum delays imposed by the laws of physics. No future technology can overcome the speed limit set by light. This fundamental constraint has forced a complete rethinking of how spacecraft navigate through potentially hazardous regions, rather than relying on real-time control from Earth. Modern spacecraft must incorporate increasingly sophisticated autonomous navigation systems capable of detecting threats and executing avoidance maneuvers without human intervention. Autonomy brings its own set of challenges. Autonomous systems must make complex decisions with limited information and computational resources. They must reliably distinguish between actual threats and sensor artifacts or noise. They must calculate optimal evasion trajectories that minimize both collision risk and fuel consumption. And they must do all this using computers that, due to the need for radiation hardening and extreme reliability, often lag years behind state-of-the-art commercial processors. The consequences of autonomous system failures become more severe the farther a spacecraft travels from Earth. When things go wrong closer to home, human controllers can intervene relatively quickly. For distant missions, a spacecraft might be on its own for hours or days while controllers analyze the problem and transmit solutions. During critical navigation scenarios, such delays could prove catastrophic. Communication bandwidth limitations further complicate remote operations. The farther a spacecraft travels from Earth, the weaker its signal becomes, reducing the data rate possible for transmissions. High-resolution images and sensor data that might help Earth-based controllers assess a complex navigation scenario must be compressed, selectively transmitted, or processed on board, potentially losing valuable details in the process. Power constraints add another dimension to the communication challenge. Transmitting signals powerful enough to reach Earth from the outer solar system requires significant energy. This creates difficult trade-offs during critical situations. Power diverted to communications might be needed for detection systems or propulsion instead, forcing mission planners to carefully prioritize spacecraft functions. The need for autonomous operation has driven significant advances in spacecraft software design. Modern space missions employ sophisticated artificial intelligence algorithms that can identify potential hazards, classify their threat level, and determine appropriate responses. These systems learn from experience, gradually improving their performance as they encounter and navigate through various situations. Redundancy becomes particularly critical when communication delays make real-time intervention impossible. Spacecraft venturing through asteroid regions typically incorporate multiple independent navigation systems, each capable of taking control if others fail. This redundancy adds mass, complexity, and cost to missions, but provides essential protection against single-point failures. Communication infrastructure also requires redundancy. Deep space missions typically rely on NASA's Deep Space Network or similar systems operated by other space agencies. With multiple ground stations positioned around Earth to maintain contact regardless of our planet's rotation, loss of communication with a spacecraft navigating through hazardous regions could leave it vulnerable precisely when guidance might be most needed. Pre-planned navigation corridors offer one approach to mitigating communication delay issues. Before launch, mission designers identify the safest paths through known asteroid distributions based on the best available data. Spacecraft then follow these predetermined routes, making only minor adjustments autonomously while reserving major course changes for situations where Earth-based controllers can be involved despite the time delay. Periodic phone-home protocols balance autonomy with oversight. Spacecraft regularly transmit status updates and navigation plans to Earth, continuing on their predetermined course unless controllers, after reviewing the data, transmit override instructions. This approach allows for human supervision while acknowledging the reality that immediate intervention is impossible. For missions involving multiple spacecraft, local communication networks can partially overcome the Earth communication delay. Spacecraft traveling in formation or distributed across a region can share sensor data and coordinate responses without involving Earth-based controllers. This distributed awareness provides better coverage and faster reaction times than any single vessel could achieve alone. Mission planners must also carefully consider what types of decisions to delegate to autonomous systems versus which to reserve for human controllers despite the time delay. Critical scientific decisions, major course changes, and responses to unusual situations typically warrant human involvement, while routine navigation adjustments and immediate hazard avoidance are necessarily delegated to onboard systems. The psychological impact of communication delay affects mission controllers as well. Operating with significant time lags requires a different mental approach than real-time control. Controllers must project forward, anticipating a spacecraft's needs hours in advance and preparing contingency plans for scenarios that might arise during periods when immediate communication is impossible. As we push the boundaries of space exploration further into the asteroid belt and beyond, the communication delay problem will only grow more significant. Future missions will likely incorporate even more advanced autonomous systems, perhaps using quantum computing, improved artificial intelligence, and better sensor fusion to navigate safely despite minimal real-time input from Earth. The fundamental physics of light-speed communication delays serves as a humbling reminder of the challenges inherent in deep space exploration. Unlike many technical obstacles that can be overcome through clever engineering, this constraint forces us to completely reconsider how we approach spacecraft control and navigation. driving innovation in autonomy that may ultimately benefit fields far beyond space exploration. The challenges of autonomous navigation necessitated by communication delays lead directly to another fundamental problem in asteroid field navigation: the limitations of propulsion and maneuverability in microgravity environments. While autonomous systems may detect hazards and calculate evasive trajectories, the physical capabilities of spacecraft to execute these maneuvers remain seriously constrained by the realities of space propulsion. Unlike aircraft or watercraft on Earth, spacecraft operate in an environment without air or water to push against. They rely entirely on the principle of action and reaction described by Newton's third law, expelling mass in one direction to move in the opposite direction. This fundamental constraint shapes every aspect of how spacecraft maneuver, particularly in emergency situations. Conventional chemical rockets, still the most common propulsion systems for spacecraft, provide powerful thrust but operate with serious limitations. They require significant propellant mass. Every kilogram of fuel carried reduces the mass available for scientific instruments, shielding, and other critical systems. Once this propellant is depleted, the spacecraft loses all ability to maneuver, regardless of what hazards it might encounter. This creates a constant tension in mission planning between carrying sufficient fuel for safety maneuvers and minimizing launch mass. Each additional kilogram of propellant requires more fuel just to launch that fuel into space, creating a compounding problem that quickly becomes prohibitive. Mission planners must carefully budget propellant, allocating specific amounts for planned maneuvers and emergency reserves. The efficiency of propulsion systems is typically measured by specific impulse, essentially how much momentum is generated per unit of propellant. Chemical rockets offer specific impulses ranging from 200 to 450 seconds, while more advanced systems like ion thrusters can achieve values above 3,000 seconds. Higher efficiency means more maneuvering capability from the same propellant mass, but comes with other trade-offs. Ion thrusters and other high-efficiency propulsion systems produce very low thrust compared to chemical rockets. While they can eventually generate significant velocity changes by operating continuously for months or years, they cannot produce the rapid acceleration sometimes needed for emergency maneuvers. A spacecraft using ion propulsion might take days to alter its trajectory significantly, useless if an asteroid is detected only hours away. This creates a dilemma for spacecraft designed to navigate asteroid environments. Chemical propulsion offers rapid response but limited total maneuvering capacity due to fuel constraints. Electric propulsion provides excellent efficiency for long-term trajectory adjustments but poor emergency response. Many missions end up incorporating both systems, further increasing complexity and mass. Beyond the propulsion systems themselves, the dynamics of movement in microgravity create additional challenges. In space, objects continue moving in the same direction until acted upon by an outside force. There's no friction to naturally slow or stabilize motion. This means that every thruster activation must be precisely calculated and often counteracted by an opposite burn to stop the resulting movement. For rotation control, spacecraft typically use reaction wheels, spinning masses that can be sped up or slowed down to alter the craft's orientation through conservation of angular momentum. These systems allow precise pointing without expending propellant but have limited capacity. When reaction wheels reach their maximum speed, they must be desaturated using thrusters, consuming precious propellant. The distribution of mass within a spacecraft significantly affects its maneuverability. Just as a diver tucks into a ball to spin faster, a spacecraft's moment of inertia determines how quickly it can rotate in response to applied forces. Mission designers must carefully consider mass distribution, often placing heavy components near the center of mass to maximize rotational responsiveness for emergency maneuvers. Another challenge in microgravity maneuvering is the phenomenon of propellant slosh. In near-weightless conditions, liquid fuel moves differently than it does under Earth's gravity, potentially shifting a spacecraft's center of mass during maneuvers. This movement can create unexpected torques and rotations, complicating precise navigation. Modern spacecraft use internal baffles and specialized tank designs to minimize this effect, but it can never be completely eliminated. The vacuum of space creates additional propulsion challenges. Without atmospheric pressure, liquids behave differently. They can spontaneously boil or freeze depending on their exposure to sunlight or shadow. Propellant management systems must carefully control temperature and pressure to ensure reliable thruster operation, adding another layer of complexity to maneuvering systems. Thermal management represents another constraint on maneuvering capability. Thrusters generate significant heat when fired, and without atmosphere to carry this heat away, spacecraft must rely on radiation for cooling. Continuous or repeated thruster operation can potentially overheat systems, limiting how frequently emergency maneuvers can be executed. For spacecraft operating in dense asteroid environments like the theoretical scenarios depicted in science fiction, the propulsion requirements would be nearly impossible to meet with current technology. The fuel needed for constant high-thrust maneuvers would far exceed practical payload capacities. This physical reality further underscores how different real asteroid navigation is from fictional portrayals. The gravitational environment around asteroids adds yet another complication to maneuvering. Larger asteroids create noticeable gravitational fields that can subtly alter a spacecraft's trajectory. These fields are typically weak, irregular due to the asteroid's uneven mass distribution, and change as the spacecraft moves relative to the asteroid. Navigation systems must account for these effects, particularly during close approaches or deliberate asteroid rendezvous missions, for future asteroid exploration and potential resource utilization. Improved propulsion technologies will be essential. Advanced concepts like nuclear thermal propulsion, solar sails, magnetoplasma dynamic thrusters, and even theoretical antimatter drives might eventually provide better combinations of thrust and efficiency. However, each potential solution brings its own engineering challenges and safety considerations. In the meantime, mission planners must work within existing constraints, developing navigation strategies that minimize the need for emergency high-thrust maneuvers. This typically means maintaining generous safety margins around known objects, traveling along pre-calculated corridors of lower asteroid density, and accepting that some level of risk is unavoidable given current propulsion limitations. The propulsion challenges of asteroid field navigation highlight an important truth about space exploration. Our ability to detect hazards has in many ways outpaced our ability to respond to them. A spacecraft might identify an approaching asteroid with perfect accuracy, yet lack the maneuvering capability to avoid it, a sobering reality that shapes every aspect of mission planning in potentially hazardous regions of space. While propulsion limitations constrain our ability to navigate around hazards in space, the physics of what happens when navigation fails and collisions occur presents an equally serious concern. Hypersonic collisions in space follow physical principles that are dramatically different from impacts we're familiar with on Earth, making them particularly destructive and difficult to protect against. In the vacuum of space, objects travel at velocities that would be impossible in Earth's atmosphere. Typical relative speeds between spacecraft and asteroids can range from 10 to 70 kilometers per second, many times faster than a bullet fired from a high-powered rifle. At these hypersonic velocities, collisions trigger physical processes more akin to explosions than conventional impacts. When objects collide at such extreme speeds, the kinetic energy is so great that it instantaneously converts solid materials into plasmas, the fourth state of matter where electrons separate from atomic nuclei. The pressure and temperature at the impact point can momentarily exceed those found in the Sun's outer layers. This is not simply an object breaking through another object. It's a violent energy conversion that vaporizes materials regardless of their strength or durability. The mathematical relationship between velocity and kinetic energy explains why these impacts are so devastating. Kinetic energy increases with the square of velocity, meaning that an object moving twice as fast carries 4 times the energy. A small pebble-sized asteroid fragment just 1 centimeter in diameter, hitting a spacecraft at 20 kilometers per second, delivers roughly the same energy as a hand grenade explosion concentrated in a tiny area. What makes hypersonic impacts particularly insidious for spacecraft protection is their unpredictability. Unlike a bullet that creates a relatively clean hole, hypersonic impacts produce secondary effects including widespread spallation, where material ejected from the backside of an impacted surface becomes a destructive spray of secondary projectiles, electromagnetic pulses from the plasma formation, and thermal radiation that can damage components far from the impact site. The behavior of materials under hypersonic impact conditions defies conventional engineering expectations. Materials that are extremely hard and durable under normal conditions may shatter catastrophically when struck at hypersonic speeds. Conversely, seemingly softer materials arranged in specialized configurations sometimes provide better protection by absorbing and distributing impact energy more effectively. This counterintuitive material behavior has led to the development of specialized shielding designs like the Whipple shield, named after its inventor, Fred Whipple. Rather than attempting to create an impenetrable barrier, these shields use multiple layers with spaces between them. The outer layer breaks up the incoming projectile into a cloud of smaller particles, which then spread out before hitting deeper layers, distributing the impact energy over a wider area. Despite these innovations, there are fundamental limits to impact protection. The mass constraints of spacecraft mean that shielding can never be comprehensive enough to stop all possible impacts. Engineers must instead focus on protecting the most critical components, accepting that some systems may be damaged or destroyed by impacts that can't reasonably be shielded against. For spacecraft navigating asteroid fields, the risk of hypersonic collisions creates a cascade of engineering challenges. Every system must be designed with potential impacts in mind. Critical components are typically given the most protection, with redundant backups placed in physically separated locations to prevent a single impact from disabling both primary and backup systems. Beyond direct impacts from asteroids or their fragments, spacecraft must also contend with secondary debris fields. When asteroids collide with each other, a rare but natural occurrence, they generate clouds of fragments travelling at various velocities. These debris fields can persist for extended periods, creating hazardous regions that may not be mapped in advance. Similarly, any impact with a spacecraft generates its own debris, potentially triggering a cascade of secondary collisions. This cascading effect reaches its theoretical extreme in the Kessler syndrome, named after NASA scientist Donald Kessler, who first described it. Although originally conceived for Earth orbit, the principle applies to any region where object density reaches a critical threshold. Once collisions become frequent enough, each impact generates debris that causes more collisions, potentially rendering entire regions of space effectively impassable. The timescale of hypersonic collisions adds another layer of complexity to protection and response. From initial impact to complete penetration of a spacecraft hull might take less than 1 microsecond, far too fast for any active response system. All protection must be passive, designed to absorb or deflect impact energy without requiring sensor detection or active countermeasures. For human missions, the consequences of hypersonic impacts become even more severe. Even small breaches in pressurized habitats can be life-threatening, and the secondary effects of impacts, including electromagnetic pulses that disable electronics and spray of secondary particles, create additional hazards for crew survival. This reality has led some experts to question whether human exploration of dense asteroid regions is feasible with foreseeable technology. Modelling and predicting hypersonic impact effects remains challenging despite advances in computational capabilities. The extreme physics involved, with materials transitioning between solid, liquid, and plasma states in microseconds, stretches the capabilities of even the most sophisticated simulation systems. Much of our knowledge comes from practical testing using light gas guns and similar facilities that can accelerate small projectiles to relevant speeds, though even these cannot fully replicate the conditions of actual space impacts. Testing the resilience of materials and designs against hypersonic impacts presents its own challenges. Ground-based facilities can only approximate space conditions and typically can't achieve the highest relative velocities encountered in actual asteroid environments. This leaves a degree of uncertainty in protection system performance that must be accounted for with additional safety margins. The study of natural impact events provides valuable data for understanding hypersonic collision physics. Micrometeoroid impacts on returned spacecraft surfaces, lunar samples, and even impact craters on Earth offer insights into how materials behave under these extreme conditions. Each new sample returned from space adds to this knowledge base, gradually improving our ability to design effective protection systems for future exploration of asteroid-rich environments. The physics of hypersonic collisions will continue to impose fundamental constraints on mission duration, spacecraft design, and acceptable risk levels. Improvements in materials science, particularly in the development of self-healing materials and advanced composite structures, may eventually provide better protection options. But the enormous energies involved in these impacts ensure that collision avoidance will always remain the preferred strategy over attempting to withstand impacts. Understanding both the limitations of spacecraft maneuverability and the devastating consequences of hypersonic collisions underscores why asteroid field navigation presents such a profound challenge. Together, these factors explain why the reckless piloting depicted in science fiction remains firmly in the realm of fantasy, and why real space exploration proceeds with careful planning and considerable caution when venturing into regions where such collisions are possible. The devastating physics of hypersonic collisions is made even more complex by the tremendous variation in the size and composition of asteroids themselves. Unlike the relatively uniform threats presented by human-made obstacles, asteroids constitute an extraordinarily diverse population of objects with properties that span enormous ranges, each presenting unique navigational challenges. The size spectrum of asteroids is truly staggering, ranging from microscopic dust particles less than a millimeter across to dwarf planets like Ceres with diameters exceeding 900 kilometers. Between these extremes lies a continuum of objects with no clear dividing lines. Traditionally, astronomers classify objects based partly on size, with meteoroids being smaller than 1 meter, asteroids ranging from 1 meter to hundreds of kilometers, and dwarf planets being the largest end of the spectrum. However, these classifications can blur at the boundaries, and what matters most for navigation is not the name we give these objects, but their specific properties. This enormous size variation creates a detection paradox for spacecraft navigation systems. Larger asteroids, while potentially catastrophic if struck, are generally easier to detect from greater distances, giving navigation systems more time to plot avoidance trajectories. The truly insidious threats often come from objects in the middle size ranges, large enough to cause significant or fatal damage to a spacecraft, but small enough to evade detection until they're dangerously close. An object just 10 centimeters across can completely destroy a spacecraft if struck at typical solar system velocities, yet such objects are extremely difficult to detect beyond short ranges. Even more concerning, there are estimated to be trillions of such objects scattered throughout the solar system. The vast majority remain untracked and essentially invisible until a spacecraft comes within detection range, which might be too late for effective avoidance maneuvers. Compounding the size challenge is the remarkable diversity in asteroid composition. Unlike the relatively homogeneous materials used in spacecraft construction, asteroids come in numerous compositional types that behave very differently during close encounters or impacts. The most common asteroid classifications include C-type, carbonaceous, S-type, silicaceous or stony, and M-type, metallic. But these broad categories contain significant internal variation and numerous subtypes. C-type asteroids, which make up about 75% of known asteroids, are dark, carbon-rich objects with relatively low density and often contain significant amounts of water in the form of hydrated minerals. S-type asteroids are brighter, composed primarily of silicate rocks and metals, while M-type asteroids contain high proportions of nickel and iron. This compositional diversity directly impacts navigation risk assessment. Metallic M-type asteroids, with their higher density, present greater danger on impact than a similarly sized but less dense C-type object. The higher albedo, reflectivity, of S-type asteroids makes them easier to detect optically than the darker C-types, which can appear almost black against the background of space. Navigation systems must account for these detection biases to avoid underestimating the presence of darker objects. The internal structure of asteroids introduces another layer of complexity. Some asteroids are solid monolithic bodies, while others are rubble piles, loose aggregations of smaller components held together primarily by gravity rather than material cohesion. During close encounters, these different structures respond differently to gravitational forces. A rubble pile asteroid experiencing stress from a spacecraft's gravity or from a minor impact might partially disintegrate, creating an unexpected debris field that poses new navigational hazards. Asteroid shape adds yet another variable to the navigation equation. Unlike the idealized spheres often depicted in educational materials, real asteroids come in highly irregular forms. Asteroid Eros resembles a peanut, while Cleopatra has been described as dog-bone-shaped. These irregular shapes create uneven gravitational fields that can affect spacecraft trajectories during close approaches. A navigation system that treats such objects as simple point masses with spherical gravitational fields might miscalculate safe flyby distances. Rotation presents additional complications. Asteroids spin at various rates, from periods of just a few minutes for small objects to several weeks for larger ones. Some, like asteroid Toutates, have complex tumbling rotations rather than spinning around a single axis. These rotational properties affect both detection, as the visible cross-section changes, and close approach dynamics. Fast-rotating asteroids can experience centrifugal forces that approach their weak gravitational binding, potentially causing surface material to detach and create localized debris clouds. Binary and multiple asteroid systems represent a special navigational challenge. Approximately 15% of near-Earth asteroids are actually pairs or groups of objects orbiting a common center of mass. These systems create complex gravitational environments and potential collision risks from multiple objects following related but distinct trajectories. The famous example of asteroid Ida and its small moon Dactyl, discovered by the Galileo spacecraft in 1993, demonstrated how these multiple systems can surprise even careful observers. Surface features like craters, boulders, and regolith, loose surface material, affect how asteroids interact with spacecraft during very close approaches or deliberate landings. The bounced landing of the Philae probe on comet Churyumov-Gerasimenko in 2014, technically not an asteroid but sharing many similar properties, demonstrated how unpredictable surface interactions can be, even with extensive advance observation. Asteroid outgassing activity further complicates navigation planning. While traditionally associated with comets, some asteroids also release dust and gas, particularly when they approach the Sun. These active asteroids, sometimes called main belt comets, can generate their own temporary atmospheres and dust clouds that extend their effective hazard radius well beyond the solid body itself. The asteroid Bennu, recently studied by NASA's OSIR-ISR-EX mission, surprised scientists by exhibiting particle ejection events that weren't predicted based on ground observations. For spacecraft designers and mission planners, this tremendous variation in asteroid properties means that detection and avoidance systems must be adaptable to a wide range of scenarios. Optical systems must function effectively against both bright and dark objects. Impact protection must consider various potential compositions and densities. Autonomous navigation algorithms must recognize and appropriately respond to unusual shapes, rotation patterns, and multiple body systems. As our exploration of the solar system continues, We're gradually building a more complete catalogue of asteroid properties through both Earth-based observation and dedicated missions like Dawn, Hayabusa, and OSIRIS-REX. Each new data point improves our understanding of asteroid diversity and helps refine navigation strategies for future missions. However, the sheer number of asteroids means that we'll never catalogue them all. Spacecraft venturing into asteroid-rich environments will always face some degree of uncertainty about what they might encounter. While navigating among the diverse population of natural asteroids presents numerous challenges, an increasingly significant concern for spacecraft operators comes from objects of our own making, space debris. This human-created hazard adds another layer of complexity to the already difficult task of navigating through asteroid-populated regions of our solar system. Space debris encompasses any human-made object in space that no longer serves a useful purpose, everything from defunct satellites and spent rocket stages to paint flakes, lost tools, and fragments from collisions or explosions. While most discussions of space debris focus on Earth orbit, where the concentration is highest, the problem extends throughout our solar system wherever human missions have ventured. The danger posed by space debris parallels that of natural micrometeoroids in many ways. Both involve relatively small objects that can cause catastrophic damage at collision velocities typical of space environments. However, debris presents unique challenges because its distribution is directly linked to human activity patterns rather than natural processes that have operated over billions of years. In Earth orbit, the debris problem has reached concerning levels, with more than 20,000 trackable objects larger than 10 centimeters and millions of smaller fragments continuously monitored by space surveillance networks. Beyond Earth orbit, our debris footprint is smaller but still significant, with spacecraft components scattered across the inner solar system and even into interstellar space. Mission planners must now account for both natural and artificial hazards when plotting trajectories through the solar system. Areas with concentrated human activity, such as common transit routes to Mars or the vicinity of popular science targets like certain asteroids or moons, have higher concentrations of human-made debris. Each mission adds to this accumulation, creating a feedback loop where today's exploration increases the navigation hazards for tomorrow's missions. The distribution pattern of human-made debris differs significantly from natural asteroid populations. While asteroids generally follow orbital patterns established over millions of years, with relatively predictable distributions, debris can appear in unusual orbits reflecting the specific missions that generated it. Debris from a Mars mission failure, for instance, might follow a trajectory that doesn't correspond to any natural population of objects, presenting an unexpected hazard in regions otherwise considered low risk. What makes debris particularly insidious from a navigation perspective is its often irregular and unpredictable nature. Natural asteroids, despite their diversity, follow physical properties and orbital mechanics that operate consistently over time. Human-made debris can include objects with highly non-natural characteristics, deployable solar panels, extending antennas, or pressurized vessels that might rupture long after being abandoned. These properties can make debris behavior after collisions or near approaches less predictable than natural objects of similar size. The smallest debris particles present perhaps the greatest navigation challenge. Particles smaller than 1 centimeter are essentially impossible to track individually with current technology, yet still carry enough kinetic energy at orbital velocities to penetrate spacecraft shielding. The distribution of these microscopic particles extends far beyond the vicinity of the objects that generated them, creating extensive clouds that can persist for years or decades. Consider the case of planetary missions that fail during orbital insertion or landing attempts. Such failures often result in spacecraft breakups that scatter components across wide regions around the target body. Future missions to these same destinations must account for this artificial debris field in addition to the natural environment. The more we explore a particular destination, the more complex its debris environment potentially becomes. Even successful missions contribute to the debris problem. Spacecraft often shed small components intentionally as part of normal operations, covers for sensitive instruments, separation mechanisms for landing systems, or material ejected during sample collection activities. The recent DART mission, which deliberately crashed into asteroid Dimorphos to test planetary defense capabilities, created a substantial debris plume that will disperse along orbital pathways throughout the inner solar system. Unlike Earth orbital debris, which we monitor extensively through radar and optical tracking systems, debris in deep space receives much less systematic tracking. Objects beyond lunar orbit are typically only tracked if they're large enough to be of scientific interest or pose a potential future hazard to Earth. This creates a significant blind spot in our space situational awareness, with countless smaller objects essentially invisible until a spacecraft encounters them directly. For mission planners, this uncertainty necessitates increasingly conservative safety margins. Trajectories must avoid not just known natural hazards, but also regions with higher probability of human-made debris based on historical mission activities. These expanded safety margins can constrain mission options, particularly for targets that have been visited multiple times previously. The time dimension adds another complication to the debris challenge. While natural asteroid populations remain relatively stable over human timescales, with some orbital evolution over centuries or millennia, debris populations can change rapidly. A single breakup event can transform a previously safe corridor into a hazardous region within minutes. Without continuous monitoring capability throughout the solar system, these sudden changes may go undetected until the next mission encounters the resulting debris field. Addressing the deep space debris challenge requires multi-layered approaches, improved tracking capabilities, with more sensitive ground-based systems and potentially space-based observation platforms, can help catalogue larger debris objects throughout the solar system. Better modelling of how debris disperses from known events can help predict regions of higher concentration. Mission design practices that minimise debris generation, such as requiring spacecraft to maintain control authority until safely disposed of at end of mission, can help prevent the problem from accelerating. Some researchers have proposed active debris removal concepts for particularly problematic regions beyond Earth orbit, though the economic and technical challenges of such approaches remain formidable. More practically, improved shielding designs and collision avoidance capabilities for future spacecraft will likely be necessary adaptations as we continue expanding our presence throughout the solar system, as exploration of asteroid-rich environments accelerates in coming decades. The intersection of natural hazards and human-made debris will present increasingly complex navigation challenges. Future mission planners will need to consider not just the natural environment of their destinations, but also the accumulated history of human activity in those regions. This growing complexity underscores the importance of international cooperation in space situational awareness and debris mitigation practices to ensure that our exploration efforts don't inadvertently make navigation through the solar system more dangerous for future missions. The challenge of navigating through both natural asteroids and human-made debris becomes even more complex when we consider another invisible but powerful factor: magnetic fields. While often overlooked in discussions of space navigation hazards, magnetic forces throughout the solar system create subtle but significant effects that can interfere with navigation systems and alter the trajectories of both spacecraft and smaller particles. Magnetic fields in space originate from multiple sources, each contributing to the complex magnetic environment that spacecraft must navigate. The Sun generates the most powerful and extensive magnetic field in our solar system, creating the heliospheric magnetic field that extends well beyond the orbit of Pluto. This solar magnetic field isn't static, but constantly changes as the Sun rotates and experiences periods of greater or lesser activity during its 11-year cycle. Solar magnetic disturbances, particularly coronal mass ejections, send powerful magnetic field fluctuations rippling through the solar system. These can temporarily alter the magnetic environment around a spacecraft, potentially affecting navigation sensors and electronic systems. During severe solar magnetic events, sensitive instruments like star trackers, often used to determine spacecraft orientation, can experience interference that compromises navigation accuracy precisely when it might be most needed for hazard avoidance. Beyond the Sun's influence, many asteroids themselves possess magnetic fields, particularly those with high metal content. M-type metallic asteroids, rich in nickel and iron, can generate local magnetic fields strong enough to be detected from orbit. The asteroid Psyche, target of an upcoming NASA mission, is believed to be the exposed metal core of a protoplanet and likely generates a significant magnetic field relative to its size. These localized asteroid magnetic fields create navigation complications that vary with distance and approach angle. As a spacecraft nears a magnetic asteroid, subtle forces may alter its trajectory in ways difficult to predict precisely without detailed advanced knowledge of the asteroid's magnetic properties, information rarely available before close approach. For precise operations like landing on or extracting samples from such bodies, these magnetic influences must be carefully modeled and compensated for. Even non-metallic asteroids can display unexpected magnetic properties. Many meteorites found on Earth, fragments of asteroids that survived atmospheric entry, contain magnetic minerals indicating that their parent bodies experienced magnetic fields during formation. The origins of these magnetized minerals remain an active area of research, suggesting that asteroid magnetic properties may be more complex and widespread than previously thought. The interaction between solar magnetic fields and asteroids creates another layer of navigational complexity. When solar wind, charged particles streaming from the Sun, encounters an asteroid, it can create a small magnetosphere or wake effect around the body. These local disturbances in the interplanetary magnetic field can extend well beyond the physical dimensions of the asteroid itself, effectively increasing the region of space where navigation might be affected. For spacecraft navigation systems, these magnetic fields present several specific challenges. Magnetometers, instruments used to measure magnetic fields, are common components in spacecraft navigation systems, helping determine orientation relative to Earth's or the Sun's magnetic field. When these instruments encounter unexpected magnetic anomalies from asteroids or solar activity, they may provide inaccurate readings that throw off the spacecraft's understanding of its position and orientation. Magnetic fields can also directly affect the trajectory of smaller debris particles, particularly those carrying an electrostatic charge. In regions with stronger magnetic fields, the paths of dust-sized particles become more complex and less predictable, potentially creating higher collision risks than models based solely on gravitational dynamics would suggest. This effect is particularly relevant for long-duration missions where cumulative small impacts can gradually degrade spacecraft components. Spacecraft themselves often generate magnetic fields through their electrical systems, creating a complex interplay between onboard electronics and external magnetic environments. Engineers must carefully design spacecraft to minimize magnetic interference with sensitive instruments, a practice known as magnetic cleanliness. Without proper magnetic shielding and design, a spacecraft's own magnetic signature might attract charged particles or interfere with navigation sensors, particularly in regions with high concentrations of conductive dust. The materials used in spacecraft construction must be selected with magnetic considerations in mind. Ferromagnetic materials that respond strongly to magnetic fields might experience subtle but cumulative forces in varying magnetic environments. For spacecraft components that need precise alignment, such as optical systems or communication antennas, even tiny magnetically induced movements can impact performance. Communication systems face their own magnetic-related challenges. Radio waves traveling through regions with varying magnetic field strengths can experience effects like Faraday rotation, which alters the polarization of the signal. For communication with Earth during critical navigation scenarios, these effects must be accounted for to ensure commands and telemetry are accurately transmitted. Future asteroid exploration missions are increasingly incorporating magnetic mapping into their scientific objectives. recognizing that understanding the magnetic properties of these bodies provides both scientific value and practical navigational benefits. The Near Shoemaker mission detected unexpected magnetic signatures from asteroid Eros, while Japan's Hayabusa 2 mission included magnetometers to study asteroid Ryugu's magnetic properties. As our exploration pushes deeper into the asteroid belt and beyond, comprehensive modelling of the solar system's magnetic environment becomes increasingly important for navigation planning. Spacecraft must be designed with greater magnetic resilience, incorporating redundant systems that can maintain accurate navigation even when primary sensors experience magnetic interference. Advanced navigation systems are beginning to incorporate real-time magnetic field mapping capabilities, allowing spacecraft to detect and adapt to magnetic anomalies as they're encountered. This adaptive approach, combined with better baseline models of expected magnetic conditions throughout the solar system, promises to reduce one more risk factor in the already complex challenge of asteroid field navigation. The magnetic complexities of asteroid environments highlight once again that safe navigation requires accounting for forces and influences beyond the simply visual or gravitational. The invisible magnetic landscape of our solar system adds subtle but significant variations to the already challenging task of plotting safe courses through fields of natural and human-made objects. While understanding and adapting to magnetic fields improves navigation safety, the frontline defense against collisions in asteroid environments comes from automatic avoidance algorithms, sophisticated software systems designed to detect potential hazards and execute evasive maneuvers without human intervention. These algorithms represent remarkable achievements in computational navigation, yet they operate under significant constraints that limit their effectiveness in real-world asteroid scenarios. Automatic collision avoidance systems typically follow a logical progression. They detect objects using onboard sensors, track their relative motion, calculate the probability of collision, determine whether evasion is necessary, compute the optimal evasion maneuver, and finally execute the chosen maneuver. While conceptually straightforward, each step in this process introduces complexities and potential failure points that affect overall system reliability. Detection capability forms the foundation of any avoidance system. The algorithms can only respond to objects they can detect, and as we've discussed earlier, many potentially dangerous objects remain undetectable until they're dangerously close. This creates a fundamental limitation. Even the most sophisticated avoidance algorithm cannot protect against objects that enter detection range with too little time for evasive action. Once an object is detected, the algorithm must determine whether it represents an actual collision threat. This involves calculating the object's trajectory relative to the spacecraft and determining whether their paths will intersect within some margin of error. This calculation itself introduces significant complexity, as it must account for gravitational influences, the spacecraft's planned maneuvers, and uncertainties in measurement. Collision probability assessment relies on statistical approaches rather than absolute certainty. For each potential hazard, the algorithm calculates a probability of collision based on the object's estimated trajectory and the uncertainties in that estimate. Setting appropriate thresholds for when to take evasive action involves difficult trade-offs. Set the threshold too low, and the spacecraft wastes precious fuel on unnecessary maneuvers. Set it too high, and it might fail to evade genuine threats. Resource optimization represents one of the most challenging aspects of avoidance algorithm design. Spacecraft have limited propellant, power, and computational resources. Each avoidance maneuver consumes some of these finite resources, potentially shortening the mission's overall duration or limiting its ability to respond to future threats. Sophisticated algorithms must balance immediate safety concerns against long-term mission sustainability, sometimes making complex value judgments about acceptable risk levels. The latency between detection and response creates another significant limitation. Even with modern computing systems, there's a processing delay between when sensors detect an object and when thrusters can begin an evasive maneuver. This delay might be just seconds or fractions of a second, but at relative velocities of kilometers per second, even small delays significantly reduce the available response window. Multi-threat scenarios pose particularly difficult challenges for avoidance algorithms. When multiple potential collision objects are detected simultaneously, the algorithm must prioritize threats and potentially plan complex maneuvers that avoid multiple objects while minimizing resource consumption. These scenarios quickly exceed the capabilities of simpler avoidance systems and require advanced computational approaches bordering on artificial intelligence. False positives present another significant challenge. Sensor glitches, cosmic ray impacts on electronic systems, or even sunlight reflecting off spacecraft components can sometimes create the appearance of hazards that don't actually exist. Avoidance algorithms must incorporate sophisticated filtering techniques to distinguish genuine threats from false alarms, all while maintaining the ability to respond quickly to real dangers. The computational requirements for effective avoidance algorithms are substantial. Calculating optimal evasion trajectories in three-dimensional space while accounting for fuel efficiency, spacecraft limitations, and multiple potential threats demands significant processing power. Yet, spacecraft computers typically lag years behind consumer technology due to the need for radiation hardening and extreme reliability. This computing constraint directly limits algorithm sophistication in practical implementations. Current automatic avoidance systems operate primarily on deterministic logic, predefined rules that dictate responses to specific situations. While effective for anticipated scenarios, these systems struggle with novel or unexpected situations. More advanced approaches using machine learning techniques show promise for developing more adaptable avoidance capabilities. But integrating AI into critical spacecraft safety systems raises significant validation and verification challenges. Testing and validating avoidance algorithms presents unique difficulties, unlike many spacecraft systems that can be thoroughly tested on Earth. The full operational environment for avoidance algorithms, featuring high-speed approaches of varied objects in microgravity, cannot be fully replicated in terrestrial test facilities. Engineers must rely heavily on simulations, with the understanding that real-world performance may differ in subtle but important ways. For human-rated spacecraft that might eventually navigate asteroid environments, avoidance algorithms must balance automation with human oversight. Too much automation might prevent human crews from understanding system decisions or intervening when necessary, while too little automation places unrealistic demands on human reaction times. This balance requires careful human-machine interface design alongside the core algorithmic development. Communication between multiple spacecraft presents an opportunity to enhance avoidance capabilities through collective detection and response planning. Distributed spacecraft networks could share sensor data and coordinate maneuvers, effectively expanding detection range and enabling more sophisticated group avoidance strategies. However, implementing such systems requires solving complex problems in real-time distributed computing and reliable space-based communication. As we develop more advanced avoidance algorithms, we encounter philosophical questions about decision-making authority. When an algorithm must choose between multiple risky options, perhaps preserving critical mission objectives at the cost of accepting higher collision risk, the values embedded in its decision-making logic become extremely important. Engineers and mission planners must carefully consider how these values are defined and implemented in systems that may someday make literal life or death decisions autonomously. Despite these limitations, automatic avoidance algorithms represent our best defense against collision threats in asteroid environments. Each generation of spacecraft features more sophisticated systems with expanded capabilities, learning from the successes and occasional failures of previous implementations. The continued evolution of these systems, incorporating advances in sensor technology, computational capabilities, and artificial intelligence, will play a crucial role in enabling safer exploration of asteroid-rich regions of our solar system. The interplay between magnetic field challenges and avoidance algorithm limitations highlights the multi-layered complexity of asteroid navigation. Each technological solution addresses specific aspects of the overall challenge, but introduces its own constraints and complications. This complex reality reinforces why the seemingly simple task of navigating among space objects remains one of the most demanding challenges in space exploration. While advanced avoidance algorithms continue to evolve as our primary defense against asteroid collisions, we must consider a critical question. What happens when humans are directly involved in navigating these hazardous environments? Despite the romantic notions portrayed in science fiction of skilled pilots manually weaving through asteroid fields, the psychological realities of human navigation in such environments reveal profound limitations that go beyond mere technological constraints. The human brain, remarkable as it is, evolved to process visual information and make spatial judgments in Earth's gravity, atmosphere, and relatively slow-moving environment. When placed in the context of asteroid field navigation, our cognitive systems face challenges that exceed their fundamental design parameters. The psychological impact of this mismatch between evolved capabilities and operational demands creates serious barriers to effective human control in asteroid environments. Perhaps most fundamental is the problem of three-dimensional spatial processing. Humans naturally struggle with truly three-dimensional navigation. On Earth, we primarily navigate in 2 dimensions with limited vertical movement. Our perceptual systems are optimized for this quasi-2D environment. In space, with objects approaching from any direction at high velocities, human operators quickly experience cognitive overload trying to track multiple objects in true 3D space. Our brains simply don't process this information efficiently enough to make split-second decisions at the speeds involved in asteroid field navigation. Depth perception presents another significant psychological challenge. On Earth, we judge distance using multiple visual cues including stereoscopic vision, perspective, atmospheric haze, relative size, and occlusion, objects blocking other objects. In the vacuum of space, many of these cues are absent or distorted. Objects don't fade with distance as they do in Earth's atmosphere. Familiar size references are missing. Without these reference points, human pilots consistently misjudge distances to objects, a potentially fatal error when calculating collision risks or evasive maneuvers. The psychological stress of space operations compounds these perceptual challenges. Extended isolation, confinement in small habitable volumes, separation from Earth, and the constant awareness of the lethal environment just beyond the spacecraft hull all contribute to psychological pressure. Studies from long-duration spaceflight show that even highly trained astronauts experience attention deficits, sleep disruption, and mood alterations after extended periods in space, all factors that would degrade performance during critical navigation tasks. The microgravity environment itself alters human sensorimotor function in ways that directly impact navigation abilities. The vestibular system, which helps maintain balance and spatial orientation on Earth, provides confusing or contradictory information in weightlessness. This sensory conflict contributes to space adaptation syndrome, commonly called space sickness, and creates persistent challenges in judging motion and orientation. For precise maneuvering tasks, this disconnect between visual perception and physical sensation creates a counterintuitive control environment that humans struggle to master even with extensive training. Time perception also operates differently under the high-stress conditions of potential collision scenarios. Research in aviation psychology demonstrates that during emergency situations, pilots often experience time compression or dilation, perceiving time as passing either more quickly or more slowly than reality. This distortion further complicates the already challenging task of judging closing speeds and response windows when objects are approaching at kilometers per second. The training challenge for preparing humans to navigate asteroid fields is particularly daunting. While flight simulators can reasonably recreate Earth aviation or even orbital maneuvering, the true conditions of high-velocity interactions with irregular asteroids in microgravity cannot be fully replicated in any Earth-based facility. Virtual reality systems offer partial solutions but cannot reproduce the actual vestibular and proprioceptive sensations of spaceflight. This training gap means that even extensively prepared human operators would face significant psychological adjustment when first confronting real asteroid field navigation. Extended space missions bring additional psychological factors that degrade navigation performance. Chronic exposure to cosmic radiation has been shown to affect cognitive function, with particular impact on executive decision-making and reaction time, precisely the capabilities needed for emergency asteroid avoidance. Circadian rhythm disruption, common in space where the normal day-night cycle is absent, further impairs attention and processing speed. The cumulative fatigue from long-duration spaceflight gradually erodes the cognitive reserves necessary for high-pressure navigation scenarios. Social psychology considerations also come into play for crewed missions. Under stress, crew dynamics can significantly impact decision-making processes. The authority gradient between commanders and subordinates might delay critical inputs during emergencies. Cultural differences in multinational crews can create miscommunications during time-critical maneuvers. Group dynamics may lead to phenomena like risky shift, where groups collectively make more dangerous decisions than individuals would make alone, particularly problematic when navigating hazardous environments. The information processing requirements for asteroid field navigation far exceed human capabilities. A pilot would need to simultaneously track multiple objects, calculate their trajectories, predict potential collision points, evaluate available evasion options, prioritize threats, and execute precise control inputs, all within seconds. This level of parallel processing simply exceeds human cognitive architecture, regardless of training or natural ability. The popular science fiction trope of the ace pilot navigating dense asteroid fields through skill alone ignores these fundamental cognitive limitations. Even the interface between human and spacecraft creates psychological complications. Control systems designed for Earth environments may not translate intuitively to space navigation. The lag between human input and spacecraft response creates a disconnected feeling that pilots find disorienting. The indirect nature of controlling a spacecraft through computer interfaces, rather than direct physical connection to control surfaces, as in atmospheric flight, creates a psychological distance that complicates intuitive operation. For all these reasons, the role of humans in asteroid field navigation has necessarily shifted towards supervision of autonomous systems rather than direct control. Human operators are increasingly cast as strategic decision-makers who set parameters, select among computer-generated options, and monitor system performance, rather than as tactical pilots directly controlling moment-to-moment maneuvering. This supervisory role aligns better with human cognitive strengths in pattern recognition, creative problem-solving, and judgment under uncertainty, while delegating the high-speed calculation and execution to automated systems. This reality represents a significant psychological adjustment for both space agencies and the public. The cultural image of the skilled human pilot deftly navigating space hazards remains powerful despite its fundamental disconnect from operational reality. For astronauts themselves, many drawn from test pilot backgrounds where direct control is highly valued, accepting this more limited navigation role requires substantial psychological adaptation. As we continue developing more advanced spacecraft capable of venturing deeper into asteroid-populated regions of our solar system, understanding these psychological limitations becomes increasingly important for mission design, crew selection, and training protocols. Rather than fighting against fundamental human cognitive constraints, effective mission planning embraces them by creating human-machine partnerships that leverage the strengths of both while compensating for their respective weaknesses in the challenging environment of asteroid field navigation. Beyond the psychological limitations of human navigation, another critical constraint on asteroid field operations involves the substantial energy requirements for executing evasive maneuvers. This often overlooked aspect of space navigation imposes harsh practical limits on how frequently and aggressively spacecraft can respond to potential collision threats, regardless of how sophisticated their detection and avoidance algorithms might be. Every change in a spacecraft's velocity or direction requires energy, typically delivered through propellant consumption. While popular depictions of spacecraft navigation might suggest unlimited maneuvering capability, the reality is that spacecraft operate under extremely tight energy budgets that directly constrain their avoidance options. Each evasive maneuver depletes finite resources that cannot be readily replenished during a mission, creating complex operational trade-offs between immediate safety and long-term mission viability. The energy cost of maneuvers scales dramatically with spacecraft mass and the desired velocity change. Basic orbital mechanics dictates that doubling the mass of a spacecraft approximately doubles the energy required for the same maneuver. Similarly, the energy requirement increases with the square of the velocity change, meaning that an evasive maneuver requiring twice the speed change demands roughly 4 times the energy. These harsh mathematical realities create strict limits on how many significant maneuvers a spacecraft can perform during its operational lifetime. Modern spacecraft use various propulsion systems, each with distinct energy efficiency characteristics that affect evasive capabilities. Chemical propulsion systems provide high thrust, enabling rapid course changes, but have relatively poor efficiency in terms of total velocity change per unit of propellant mass. Ion propulsion and other electric propulsion technologies offer much higher efficiency but produce very low thrust levels, making them excellent for gradual, planned trajectory adjustments, but nearly useless for emergency evasion of suddenly detected objects. This propulsion dichotomy creates a difficult design trade-off. Spacecraft optimized for efficient travel between destinations, typically using low thrust, high-efficiency propulsion, are inherently less capable of rapid evasive maneuvers. Conversely, vessels equipped with powerful chemical thrusters for emergency avoidance carry a significant mass penalty that reduces their overall range or scientific payload capacity. Many modern missions attempt to incorporate both systems, but this hybrid approach increases complexity, cost, and mass. Energy storage represents another critical constraint. Spacecraft typically generate power through solar panels in the inner solar system or radioisotope thermoelectric generators in the outer solar system where sunlight is insufficient. This power generation capacity is carefully budgeted across all spacecraft systems, with margins typically measured in watts rather than kilowatts. Electric propulsion systems, which might be used for gradual avoidance maneuvers, draw substantially from this limited power budget, potentially requiring other systems to be temporarily deactivated during thruster operation. Battery capacity further limits rapid response capability. While batteries can provide temporary power surges beyond what generation systems produce, their capacity is strictly limited by mass constraints. A spacecraft executing multiple energy-intensive maneuvers in quick succession might fully deplete its batteries, leaving insufficient power for critical systems like thermal control, communications, or the very sensors needed to detect additional hazards. Mission planners must carefully allocate this limited energy storage capacity, ensuring sufficient reserves for both planned operations and emergency scenarios. The cumulative nature of energy expenditure creates particularly challenging long-term constraints. Early in a mission, controllers might be willing to execute energy-intensive avoidance maneuvers when facing uncertain risks. However, as propellant is consumed and systems gradually degrade, the energy cost of each maneuver must be weighed more carefully against diminishing reserves. Late mission operations often feature much more conservative decision thresholds, accepting slightly higher collision risks to preserve remaining energy resources. This energy conservation necessity drives the development of increasingly sophisticated trajectory optimization algorithms, rather than simple avoidance maneuvers that might waste significant propellant. Modern spacecraft employ complex path planning that attempts to minimize energy expenditure while maintaining adequate safety margins. These algorithms consider not just the immediate hazard, but the entire anticipated trajectory, sometimes accepting slightly closer approaches to some objects to enable more efficient overall avoidance paths. The energy requirements for avoidance maneuvers also vary substantially with warning time. With early detection of a potential hazard, a spacecraft can typically execute a small, efficient course adjustment that compounds over time into a significant deviation from the collision course. Late detection scenarios force much more energetically expensive maneuvers to achieve the same missed distance. This relationship creates a direct connection between detection capability and energy efficiency. Better sensors effectively reduce propulsion requirements by enabling earlier, more efficient adjustments. For crewed spacecraft, life support considerations further complicate energy management during avoidance maneuvers. Human-rated vessels must maintain acceptable temperature, pressure, and air quality regardless of other operational demands. These non-negotiable requirements create an energy consumption floor that cannot be reduced, limiting the power available for propulsion and other systems during emergency operations. Additionally, life support redundancy requirements typically increase overall spacecraft mass, further increasing the energy needed for effective maneuvering. The harsh radiation environment of space gradually degrades energy systems over time, creating another constraint on long-duration missions. Solar panels slowly lose efficiency due to micrometeoroid impacts and radiation damage. Battery capacity diminishes with each charge-discharge cycle. Propellant tanks may develop small leaks. Thruster performance degrades with use. These cumulative effects mean that a spacecraft's energy budget for avoidance maneuvers typically shrinks throughout its operational lifetime, requiring increasingly conservative hazard assessment as a mission progresses. Remote operations in deep space introduce additional energy challenges related to communications. Maintaining contact with Earth requires power for radio or laser communication systems, with power requirements increasing dramatically with distance. During complex avoidance scenarios, the ability to transmit detailed sensor data and receive guidance from mission control competes with the energy needed for the avoidance maneuvers themselves. This communication energy requirement becomes particularly significant in scenarios involving multiple simultaneous hazards where Earth-based supercomputers might provide valuable trajectory analysis if sufficient data can be transmitted. Future technologies offer potential solutions to these energy limitations. Advanced propulsion concepts like nuclear thermal propulsion could provide both high thrust and improved efficiency. More efficient solar cells and advanced radioisotope power systems could increase available power. Improved battery technologies might enable more energetic burst operations. However, all space systems will continue operating under strict energy constraints imposed by fundamental physics and practical engineering limitations. Understanding these energy constraints provides important context for why asteroid field navigation remains challenging despite advances in detection technology and avoidance algorithms. Even perfect hazard detection provides limited safety if a spacecraft lacks the energy resources to effectively respond to identified threats. As we push further into asteroid-populated regions of our solar system, energy management will remain one of the most critical aspects of mission planning and operations, fundamentally shaping how we approach the navigation challenge in these complex environments. The energy constraints of spacecraft maneuvering directly influence one of the most crucial aspects of asteroid field navigation: the fundamental design of the vessels themselves. Creating spacecraft capable of safely traversing asteroid-populated regions requires specialized design approaches that balance multiple competing priorities, often forcing engineers to make difficult compromises between safety, mission capability, and practical feasibility. The most basic design consideration involves the physical configuration of the spacecraft itself. The shape, size, dot, and structural layout dramatically affect vulnerability to impacts and ability to execute avoidance maneuvers. Compact designs with minimal cross-sectional area reduce the statistical probability of collision, following the simple principle that smaller targets are harder to hit. However, this compactness must be balanced against operational requirements like solar panel area, instrument deployment needs, and thermal management considerations. Spacecraft orientation presents another key design factor. Many modern deep space vessels are designed to maintain specific orientations relative to the Sun or Earth for power generation and communication purposes. This directional dependence creates inherent blind spots in sensor coverage and can restrict maneuverability during hazard avoidance scenarios. More advanced designs incorporate multiple sensor arrays and thruster configurations that allow for effective operation and maneuvering regardless of orientation. But these redundancies add mass and complexity to the system. Thus, shield design represents perhaps the most direct response to collision hazards. Modern spacecraft incorporate specialized shields, often based on the Whipple shield concept, multiple layers of material separated by space, designed to break up and disperse impact energy rather than simply trying to stop it. These shields can effectively protect against smaller particles but add considerable mass to the spacecraft. The shield mass/protection trade-off becomes a central design challenge, with engineers carefully analysing expected debris environments to optimise protection without excessive weight penalties. Material selection plays a crucial role in both shield effectiveness and overall spacecraft resilience. Traditional aerospace materials like aluminum offer reasonable protection at moderate weight, but advanced composites, ceramic matrices, and metallic foams can provide superior impact resistance for the same mass. Some cutting-edge designs incorporate self-healing materials that can automatically seal small penetrations, preventing the catastrophic pressure loss that would otherwise follow a micrometeoroid puncture of a pressurized habitat or fuel tank. The distribution of critical components throughout the spacecraft represents another key design strategy for asteroid field navigation. Rather than concentrating vital systems in a single location, modern designs distribute essential components and incorporate multiple redundant backups physically separated from each other. This approach ensures that a single impact, even if it penetrates shields and damages one system, is unlikely to disable all instances of that critical function. Power system design faces particular challenges for asteroid field navigation. Solar panels present large, vulnerable surfaces that are difficult to effectively shield without blocking incoming light. Radioisotope power systems offer better protection potential but provide limited power. The need for continuous, reliable power to operate detection and avoidance systems creates a difficult design problem where the very systems generating power are among the most vulnerable to impact damage. Advanced designs incorporate emergency backup power sources and rapid reconfiguration capabilities to maintain essential functions even after significant panel damage. Propulsion system layout involves similar vulnerability considerations. Exposed thruster nozzles, fuel lines, and pressurized tanks represent potential single-point failure areas that could disable maneuvering capability if damaged. Distributed propulsion systems with multiple independent thruster clusters provide greater resilience but increase system complexity and mass. Some advanced concepts incorporate adjustable thrust vectoring that maintains maneuvering capability even if some thrusters are disabled, allowing continued controlled flight despite partial propulsion system damage. Thermal management presents a particularly complex design challenge for asteroid field navigation. Spacecraft require precise temperature control for electronics, propellants, and crew habitats, if applicable, typically managed through radiators that emit excess heat into space. These radiators, like solar panels, present large, vulnerable surfaces that are difficult to shield effectively. Impact damage to thermal control systems can lead to cascading failures as components overheat or freeze, potentially disabling the entire spacecraft. Redundant. Physically separated thermal pathways and self-adjusting systems help mitigate this vulnerability. For crewed spacecraft, habitat design introduces additional considerations beyond what applies to robotic missions. Human habitats require not just protection from catastrophic penetration, but also shielding against radiation exposure that would increase substantially following even minor hull damage. Layered designs with separate pressure vessels, emergency isolation capabilities for damaged modules, and rapid seal systems for small breaches become essential features. The psychological aspects of habitat design also matter. Crew quarters positioned toward the center of the spacecraft not only offers better physical protection but can reduce anxiety about potential impacts. Sensor integration throughout the spacecraft structure enables another critical design approach: real-time structural health monitoring. By embedding networks of acoustic, strain, temperature, and pressure sensors throughout the vessel, modern designs can instantly detect, locate, and characterize impact damage. This information allows for immediate assessment of structural integrity and guides automated responses or crew actions to address the specific damage. These distributed sensor networks serve both safety and maintenance functions, allowing spacecraft to operate more safely despite accumulating minor damage over extended missions. Communication system design for asteroid field navigation prioritizes reliability under adverse conditions. Multiple independent antennas, variable power transmitters, and diverse communication pathways ensure that contact with Earth or other spacecraft can be maintained even after partial system damage. For deep space missions, where communication latency makes real-time Earth control impossible, robust local communication networks between distributed spacecraft components or multiple cooperating vessels become essential for coordinated hazard response. Data systems for asteroid field navigation require particular attention to radiation hardening and fault tolerance. The same high-energy particles that pose physical dangers to spacecraft components can cause data corruption or system crashes at critical moments. Multiple redundant computers running diverse software implementations of critical navigation functions provide protection against both physical damage and software failures. Some advanced designs incorporate physically isolated safe mode computers with minimal, thoroughly verified software that can maintain basic navigation and hazard avoidance while primary systems are recovered. The mass constraints of spaceflight create perhaps the most fundamental design challenge for asteroid field navigation. Every protective feature, redundant system, and safety margin adds mass that must be launched from Earth at enormous expense. Engineers must carefully prioritize which hazards receive the most robust protection, which systems get the most redundancy, and which capabilities are truly essential versus merely desirable. This harsh reality of mass constraints often forces designers to accept certain vulnerabilities as unavoidable, focusing protection on ensuring mission-critical capabilities survive even if secondary objectives must be sacrificed. Manufacturing and testing considerations also influence spacecraft design for asteroid environments. Systems must not only perform well on paper, but must be buildable using available materials and technologies, verifiable through practical test methods, and maintainable during the mission lifetime. The inability to fully test asteroid impact scenarios at true space velocities means designs must rely heavily on simulation and scaled testing, introducing unavoidable uncertainties that typically lead to more conservative design margins. As we push deeper into asteroid-rich environments, these design considerations will continue evolving based on operational experience and technological advances. Each mission into challenging environments provides valuable data about which design approaches worked well and which vulnerabilities proved most problematic. This continuous learning process drives the gradual evolution of spacecraft design, steadily improving our ability to navigate safely through the hazardous regions that contain so many scientific treasures and potential resources. While specialized physical design provides the hardware foundation for asteroid field navigation, increasingly sophisticated software systems represent the intelligence that enables effective hazard avoidance. Artificial intelligence has emerged as a critical technology for advanced space navigation, offering capabilities that fundamentally change how spacecraft can perceive, understand, and respond to complex asteroid environments. Traditional spacecraft control software relies primarily on predetermined rules and procedures, executing fixed responses to anticipated situations, while effective for well-understood scenarios. This approach struggles with the unpredictable nature of asteroid field navigation, where each situation may be unique. AI systems, by contrast, can analyze novel situations, identify patterns, and generate appropriate responses without being explicitly programmed for every possible scenario. This adaptability makes AI particularly valuable for missions venturing into poorly mapped regions where unexpected hazards may appear with little warning. The application of AI to space navigation begins with perception, the processing and interpretation of sensor data. Modern deep learning systems can analyze multiple data streams from radar, LiDAR, optical cameras, and other sensors to identify potential hazards that might be missed by traditional detection algorithms. These systems are particularly effective at distinguishing actual objects from sensor artifacts, reducing false positives that would otherwise trigger unnecessary evasive maneuvers and waste precious propellant. Beyond simply detecting objects, AI excels at trajectory analysis and risk assessment. Machine learning algorithms can rapidly process historical tracking data to predict how objects will move, accounting for complex factors like irregular shapes, rotation, dot, and gravitational interactions that traditional physics models might oversimplify. When multiple potential hazards are present, AI systems can perform complex probability calculations to identify which objects present genuine threats requiring evasion and which will naturally pass at safe distances. Path planning represents another area where AI dramatically outperforms conventional software. When evasive action is necessary, AI algorithms can generate optimal trajectories that avoid multiple hazards while minimizing propellant usage and maintaining critical spacecraft orientations for power and communication needs. These systems can evaluate thousands of potential paths in seconds, identifying solutions that human operators or rule-based systems might miss entirely. The resulting flight paths often appear counterintuitive but prove mathematically optimal when analyzed in detail. Decision-making under uncertainty is perhaps AI's most valuable contribution to asteroid field navigation. Space operations inherently involve incomplete information, sensors have limited range and accuracy, object properties remain partially unknown, and future conditions can only be predicted within probability ranges. Traditional software struggles with these uncertainties, typically defaulting to worst-case assumptions that lead to overly conservative operations. AI systems can reason probabilistically, making nuanced, risk-weighted decisions that better balance safety against mission objectives. The implementation of AI for space navigation faces significant technical challenges, particularly regarding computational resources. The radiation-hardened computers qualified for spaceflight typically offer processing power orders of magnitude below what's available in terrestrial systems. AI developers must create highly optimized algorithms that deliver sophisticated capabilities within these severe computational constraints. Specialized hardware like radiation-tolerant graphics processing units and field-programmable gate arrays increasingly supplement traditional spacecraft computers, providing the parallel processing capabilities that many AI algorithms require. Verification and validation of AI systems present another major challenge. Traditional spacecraft software undergoes exhaustive testing to verify that it handles all anticipated conditions correctly. AI systems, particularly those using neural networks or other machine learning approaches, operate through complex internal representations that cannot be easily inspected or verified through traditional methods. Space agencies have developed specialized testing frameworks that combine simulation-based training, formal mathematical verification where possible, and graduated deployment strategies that initially limit AI authority while building operational confidence. The balance between automation and human oversight represents a key consideration in space AI implementation. For nearby missions where communication latency is minimal, AI systems often function as decision support tools, generating recommendations for human operators to approve. As missions venture deeper into the solar system where communication delays make real-time human supervision impossible, AI must operate with increasing autonomy. This progression requires careful calibration of when and how AI systems should request human input versus making independent decisions based on pre-established parameters. Learning and adaptation during missions offer particularly promising capabilities for asteroid field navigation. Early AI systems were effectively fixed after launch, but modern approaches incorporate continuous learning that allows navigation systems to improve based on operational experience. A spacecraft encountering unexpected phenomena in an asteroid field can adapt its detection and avoidance strategies based on what worked effectively in previous encounters. This learning capability proves especially valuable for long-duration missions where conditions may change substantially over time. Collaborative AI across multiple spacecraft represents an emerging frontier in asteroid field navigation. Rather than relying on a single vessel's limited sensor range and processing power, distributed networks of spacecraft can share detection data, coordinate observations from multiple angles, and collectively map hazardous regions. The resulting shared environmental awareness enables more effective navigation for the entire group. These collaborative approaches require sophisticated AI systems that can maintain coherent operation despite communication limitations and potential disagreements between individual vessels' observations. The ethical implications of AI for space navigation, while less immediately visible than technical challenges, nevertheless require careful consideration. As AI systems gain greater autonomy, they increasingly make value-weighted decisions balancing scientific return against equipment safety or, in crewed missions, human safety. The values embedded in these decision-making frameworks, often implicitly through training data and reward functions rather than explicit programming, effectively encode human priorities into machines that may operate for years beyond direct human control. Ensuring these systems reflect appropriate priorities requires involving not just engineers but also ethicists, mission stakeholders, and in some cases, representatives from the broader public. Natural language interfaces between humans and AI navigation systems are becoming increasingly important, particularly for crewed missions. Rather than requiring astronauts to understand complex technical details of navigation algorithms, modern AI systems can explain their reasoning and recommendations in conversational language, making their decision processes transparent and accessible. This capability proves especially valuable during high-stress scenarios where clear communication about navigation options and risks becomes critical for effective human-machine collaboration. The future trajectory of AI in space navigation points toward increasingly capable systems that combine multiple AI approaches rather than relying on single techniques. Hybrid systems integrating rule-based expert systems, machine learning, evolutionary algorithms, and formal logical reasoning can leverage the strengths of each approach while compensating for individual weaknesses. These integrated systems may eventually approach true general problem-solving capabilities, able to handle entirely novel situations with human-like creativity while maintaining machine-like precision in execution. As we contemplate more ambitious missions to asteroid-dense regions like the Main Belt or Trojan populations, advanced AI for navigation will transition from being merely beneficial to becoming absolutely essential. The combination of distance from Earth, complex hazard environments, and the need for resource-efficient operation will require autonomous capabilities far beyond what traditional software can provide. In this sense, the future of asteroid field navigation and the development of space-qualified AI are fundamentally linked, each driving the other forward as we push the boundaries of solar system exploration. The theoretical advances in artificial intelligence for space navigation, while impressive, build upon a foundation of hard-won practical experience from actual missions to asteroid environments. Over the past few decades, a series of increasingly ambitious spacecraft have ventured into asteroid-rich regions, each encountering unexpected challenges that have reshaped our understanding of the navigation problem. These historical lessons provide crucial context for evaluating current approaches and developing future strategies. The modern era of asteroid exploration began with NASA's Galileo spacecraft, which conducted flybys of asteroids Gaspra in 1991 and Ida in 1993 while en route to Jupiter. These encounters, though brief, delivered several surprising insights. Engineers had planned Galileo's trajectory based on ground-based observations of the asteroids, but upon approach, the spacecraft revealed that both objects were significantly more irregular in shape than anticipated. Ida's unexpected companion moon Dactyl, the first asteroid moon ever discovered, demonstrated that even well-observed asteroids could harbour surprises that might affect navigation safety. These early flybys underscored the limitations of Earth-based observations for detailed mission planning. The Near-Shoemaker mission, launched in 1996, provided the next significant leap in asteroid navigation experience. After a successful flyby of asteroid Matilda, the spacecraft experienced a critical software failure during its first attempted orbital insertion around asteroid Eros. A main engine burn aborted prematurely, triggering emergency shutdown of the spacecraft's systems and causing communication loss for over 24 hours. When contact was eventually re-established, the mission team had to design an entirely new approach trajectory, delaying the rendezvous by a year. This incident highlighted the criticality of fault-tolerant software and robust contingency planning for asteroid missions. A navigation failure in deep space might allow for recovery, but only with significant mission impact. When Near finally reached Eros in 2000, another navigation lesson emerged. The irregular gravity field around the asteroid proved much more complex than models had predicted, complicating orbital maintenance. The mission team had to develop new gravity mapping techniques in real time, gradually refining their navigation models as the spacecraft spiraled closer to the surface. This experience demonstrated that effective navigation in asteroid environments requires adaptive approaches that can incorporate new data to continuously improve navigational models during the mission itself. Japan's Hayabusa mission to asteroid Itokawa, launched in 2003, encountered a cascade of technical problems that tested the limits of asteroid navigation. Solar flare damage to its solar panels reduced available power. Multiple reaction wheels failed, limiting attitude control, and fuel leaks compromised its propulsion system. Despite these setbacks, the mission team developed innovative workarounds, including using ion engines in ways they weren't originally designed for, eventually achieving a landing on the asteroid's surface. The mission demonstrated that navigation success often depends not just on pre-planned approaches, but on creative problem-solving when facing the unexpected degradation of spacecraft capabilities, a particularly valuable lesson given the harsh environment of asteroid regions. The European Space Agency's Rosetta mission, while targeting a comet rather than an asteroid, provided relevant lessons for small-body navigation. Upon arrival at Comet Churyumov-Gerasimenko in 2014, controllers discovered an irregular object with much higher surface variance than expected. The Philae lander bounced several times before coming to rest in an unplanned location due to the failure of its anchoring systems. This experience highlighted how surface properties of small bodies can defy expectations based on remote observations, requiring navigation and landing systems with broader operating parameters than might seem necessary based on pre-mission modelling. NASA's Dawn mission, which orbited both asteroid Vesta and dwarf planet Ceres between 2011 and 2018, demonstrated the navigation challenges of transitioning between different asteroid environments. The substantially different masses, shapes, and surface features of these two bodies required distinct navigation approaches despite using the same spacecraft. Dawn's ion propulsion system proved valuable for orbital adjustments, but required longer lead times for trajectory changes compared to traditional chemical propulsion. This highlighted the trade-off between efficient propulsion options that extend mission duration versus rapid response capabilities for hazard avoidance. The OSIR-ISR-EX mission to asteroid Bennu, arriving in 2018, encountered perhaps the most surprising asteroid environment yet. Initial observations revealed a surface far more boulder-strewn than anticipated, with few suitable sites for the planned sample collection. Additionally, controllers observed unexpected particle ejection events, small eruptions of material from the asteroid's surface that created transient clouds of debris around Bennu. These findings forced a complete reassessment of the mission's sampling strategy and demonstrated that asteroids can exhibit dynamic environmental changes that affect navigation safety, not just static hazards. Japan's Hayabusa 2 mission to asteroid Ryugu, operating from 2018 to 2019, successfully deployed multiple small rovers and landers to the asteroid's surface. The mission implemented an artificial crater creation experiment, using a small carried impactor to expose subsurface material. These operations required precise navigation in close proximity to the asteroid, with careful timing to avoid debris from the impact. The mission's success demonstrated the feasibility of complex, multi-phase operations near asteroids when backed by sufficient redundancy and contingency planning. Collectively, these missions reveal several consistent patterns about asteroid navigation. First, nearly every asteroid encounter has delivered surprises that required mission adaptations, from unexpected shapes and densities to surface properties and gravitational fields that defied pre-mission models. Second, spacecraft degradation in the asteroid environment has frequently forced operations teams to develop workarounds that weren't anticipated during mission planning. Third, communication constraints and light time delays have consistently emphasized the value of onboard autonomy for rapid decision-making during critical phases. Perhaps most importantly, these historical missions demonstrate the progressive learning curve in asteroid navigation. Each mission has built upon the experiences of its predecessors, gradually expanding our capabilities from brief flybys to extended orbital operations, surface landings, sample collection, and even controlled impact experiments. This progression hasn't been without setbacks. Nearly every mission mentioned experienced significant anomalies or failures, but the overall trajectory shows steady improvement in our ability to navigate these challenging environments. Current missions like NASA's Lucy, exploring Jupiter's Trojan asteroids, and Psyche, targeting a metal-rich asteroid, will further extend this experience base to new asteroid populations with distinct properties. Each will likely encounter its own unique challenges that will inform future mission design. The lessons from these historical missions have directly shaped current spacecraft design approaches, navigation strategies, and mission planning methodologies, creating a valuable experiential foundation that complements theoretical advances in fields like artificial intelligence. While these historical lessons have significantly improved our understanding of asteroid navigation challenges, one persistent complication continues to affect spacecraft operations in these environments: the pervasive presence of cosmic dust. This seemingly minor factor creates outsized problems for the sensitive instruments that spacecraft rely on for safe navigation. Cosmic dust, microscopic particles typically smaller than 100 micrometers in diameter, exists throughout our solar system, with particularly high concentrations in the asteroid belt and near comets. These tiny particles originate from asteroid collisions, comet outgassing, and interstellar sources, creating a diffuse but ever-present cloud through which spacecraft must travel. Despite their minuscule size, these dust particles create serious navigation challenges through their cumulative effects on spacecraft instrumentation. Optical navigation systems are perhaps most directly affected by cosmic dust exposure. Spacecraft typically rely on cameras with precision optics to identify and track asteroids, stars, and other reference points. Over time, dust impacts on these optical surfaces cause erosion through a process called pitting, where each tiny particle removes a microscopic amount of material. The cumulative effect gradually degrades optical clarity, reducing contrast and creating scattered light that interferes with precise observations. Even a single larger dust particle striking a camera lens at high velocity can create a substantial impact crater that distorts images in ways that might confuse automated navigation algorithms. Protective covers for optical instruments provide only partial solutions. While they can shield lenses during periods of higher dust exposure, they must be opened for the instruments to function. Each opening and closing cycle introduces mechanical wear and creates additional opportunities for dust to enter the system. Some advanced designs incorporate transparent protective windows that remain in place permanently. But these windows themselves become degraded by dust impacts, eventually requiring their own replacement or cleaning, operations that are rarely possible in deep space missions. Solar panels, crucial for spacecraft power generation, face similar degradation from dust impacts. As microscopic pits accumulate on panel surfaces, they scatter incoming sunlight rather than allowing it to reach the photovoltaic cells beneath. This scattering reduces power generation efficiency, a particular concern for missions using electric propulsion systems that require substantial power for operation. The gradual power reduction can force operational compromises, potentially limiting the energy available for navigation systems precisely when they might be most needed in hazardous environments. Star trackers, specialized cameras that identify star patterns to determine spacecraft orientation, are especially vulnerable to dust-related navigation errors. These instruments rely on precise pattern matching between observed stars and onboard catalogues. Dust impacts that create small bright spots on optical components can be misinterpreted as stars, confusing the pattern-matching algorithms and potentially causing orientation errors that propagate through the entire navigation system. For critical maneuvers near asteroids, even small orientation uncertainties can translate to dangerous position errors. Thermal control surfaces also suffer from dust erosion effects. Spacecraft maintain operational temperatures through carefully balanced heat absorption and radiation, typically using specialized coatings with specific thermal properties. Dust impacts gradually alter these properties, changing how surfaces absorb and emit heat. The resulting thermal imbalances can affect electronic components, potentially causing sensor calibration drift or even failure of navigation computers if temperatures exceed operational limits. Radio frequency antennas used for communication with Earth and for radar navigation systems experience similar degradation. Dust impacts on dish surfaces reduce signal quality over time, decreasing data transmission rates and potentially limiting the ability to receive command updates or transmit navigation sensor data back to mission controllers. For radar systems used to map nearby asteroids, this degradation can reduce effective range and resolution, constraining the spacecraft's ability to detect smaller hazards at safe distances. The mechanical components of navigation systems aren't immune to dust effects either. Reaction wheels used for attitude control, gimbal motors that point instruments, and deployment mechanisms for solar arrays all contain moving parts susceptible to dust contamination. If dust particles enter these mechanisms, they can increase friction, cause premature wear, and eventually lead to reduced performance or complete failure. Spacecraft designers implement extensive sealing and lubrication strategies to mitigate these risks, but perfect protection remains elusive in the dusty environment of asteroid regions. The insidious nature of dust-related degradation lies in its gradual, cumulative impact. Unlike catastrophic failures that occur suddenly and trigger immediate response protocols, dust effects typically manifest as slow performance declines across multiple systems. This degradation can be difficult to distinguish from other aging effects, complicating diagnostic efforts and potential mitigation strategies. Mission planners must build substantial margins into all systems to account for this expected degradation over the mission lifetime. Dust particles also present a unique navigational hazard through their electrostatic properties. In the space environment, dust frequently acquires electrical charge through solar radiation exposure. These charged particles can be attracted to spacecraft surfaces through electrostatic forces, potentially accumulating in higher concentrations than the surrounding space would suggest. This accumulation can cause unexpected electrical discharge events that might temporarily disrupt sensitive navigation electronics or create false readings in sensor systems. The distribution of cosmic dust isn't uniform throughout asteroid environments, creating additional navigation planning challenges. Dust density typically increases near active asteroids that might be outgassing or shedding surface material, in the vicinity of recent asteroid collisions, and along the orbital paths of comets that regularly shed material. These high-density regions might require special operational protocols, such as temporarily powering down sensitive systems or orienting the spacecraft to minimize exposure of critical components. Research into dust mitigation strategies continues to advance, with several promising approaches under development. Electrostatic dust shields use electrical fields to repel charged particles away from sensitive surfaces. Self-healing materials can partially recover from dust impact damage. Dust-tolerant optical designs incorporate multiple light paths and automated calibration procedures that can compensate for gradual degradation. Active cleaning mechanisms, though challenging to implement in the space environment, might eventually provide ways to restore degraded surfaces during extended missions. For future asteroid belt missions, understanding and mitigating dust effects will remain a critical aspect of navigation system design. As mission durations extend from months to years or even decades, the cumulative impact of dust exposure becomes increasingly significant. Navigation strategies must incorporate not just the current state of instruments, but their projected future performance as dust effects accumulate. This forward-looking approach requires sophisticated degradation modeling based on dust density measurements from previous missions and laboratory simulations of long-term exposure effects. The ubiquitous presence of cosmic dust serves as a humbling reminder that even the most sophisticated navigation technologies must contend with the fundamental physical realities of the space environment. While less visually dramatic than asteroid collisions, the persistent erosion caused by these tiny particles represents one of the most consistent and unavoidable challenges to long-term operations in asteroid regions. The persistent challenges posed by cosmic dust highlight why effective training and simulation systems are essential for preparing both human operators and autonomous systems to navigate asteroid environments successfully. Given the impossibility of replicating actual asteroid conditions on Earth, simulation technologies have become the cornerstone of preparation for missions venturing into these hazardous regions. Creating effective training environments for asteroid navigation begins with the fundamental challenge of accurately representing the physical conditions spacecraft will encounter. Unlike aircraft or maritime simulators, which can draw on extensive real-world operational data, asteroid environment simulators must extrapolate from limited observational data and physical models. The microgravity conditions, vacuum environment, and extreme velocities involved cannot be directly replicated in terrestrial facilities, forcing reliance on computational simulation for many aspects of training. Visual simulation presents particular difficulties. The stark lighting conditions in space, with extreme contrasts between sunlit and shadowed surfaces, create visual environments unlike anything experienced on Earth. Asteroids typically have very low albedo, reflectivity, appearing as dark, low-contrast objects against the black background of space. Accurately reproducing these visual characteristics requires sophisticated rendering systems that go beyond conventional computer graphics approaches. Modern simulators employ physically based rendering techniques that model how light actually interacts with different materials under space conditions, providing more realistic training for both human operators and computer vision systems. Gravitational dynamics around irregular-shaped asteroids create another simulation challenge. Unlike the well-understood gravitational fields of planets and moons, asteroids produce complex, irregular fields that vary significantly with distance and relative position. Small changes in spacecraft location can result in unexpectedly large changes in gravitational influence. Advanced simulators now incorporate detailed mathematical models based on actual mission data from previous asteroid encounters, allowing more accurate prediction of orbital dynamics and trajectory evolution around these irregular bodies. Simulating sensor performance under asteroid environment conditions requires particular attention to detail. Each sensor type, optical cameras, LiDAR, radar, star trackers, has unique response characteristics affected by the space environment. Modern training systems model not just ideal sensor performance, but the degraded operation that occurs due to radiation exposure, temperature fluctuations, and the dust effects discussed previously. This degradation modeling is crucial for realistic training, as navigation often depends more on handling imperfect sensor data than on operations under ideal conditions. Communication delays represent another crucial aspect of asteroid navigation simulation. Training systems must incorporate the light time delays that make real-time control from Earth impossible for deep space missions. These delays force operators to develop different control strategies than would be used for near-Earth operations. Advanced simulators include configurable delay settings that can represent different mission phases and distances, allowing operators to practice the anticipatory control techniques required when commands take minutes or hours to reach the spacecraft. For human operators, psychological fidelity in simulation has proven as important as physical accuracy. The stress, isolation, and high-stakes decision environment of actual space missions significantly impact human performance. Modern training approaches incorporate elements of this psychological reality through techniques like sleep deprivation during extended simulation runs, unexpected failure injections, and time-pressured decision scenarios. These approaches help prepare operators for the cognitive and emotional challenges they'll face during actual missions, beyond just the technical aspects of navigation. Hardware-in-the-loop simulation has emerged as a particularly valuable approach for asteroid mission preparation. This technique connects actual flight computers and sometimes physical hardware components to simulation environments, allowing real flight software to interact with simulated sensor inputs and environmental conditions. This approach validates both the hardware and software systems under conditions as close to mission reality as possible without actually flying in space. The OSIRIS-REx mission used extensive hardware-in-the-loop testing to validate its autonomous navigation systems before attempting its complex sample collection maneuver on asteroid Bennu. Mission control team training represents another crucial simulation application. Modern asteroid missions involve large teams of specialists who must coordinate effectively during critical navigation phases. Simulation facilities like NASA's Mission Control Training Facility allow these teams to practice coordinated responses to complex scenarios, developing the communication protocols and decision-making frameworks that become essential during actual operations. These simulations typically include intentionally incomplete information and ambiguous sensor data to replicate the uncertainty of real asteroid encounters. Virtual reality and augmented reality technologies have revolutionized certain aspects of asteroid navigation training. VR systems allow operators to experience three-dimensional representations of asteroid environments from different perspectives, developing better spatial awareness of the complex shapes and surface features that affect close proximity operations. AR systems can overlay trajectory projections and hazard indicators on simulated or actual spacecraft camera feeds, helping operators develop the visualization skills needed to interpret complex spatial relationships quickly and accurately. Machine learning has transformed how simulation environments are developed and used for training. Rather than manually creating scenarios, AI systems can generate thousands of varied training situations that systematically challenge different aspects of navigation performance. This approach is particularly valuable for training autonomous navigation systems, as it can expose them to a much wider range of potential scenarios than human programmers could reasonably anticipate and code explicitly. The resulting training provides more robust performance when encountering novel situations during actual missions. Physics-based simulation of impact events and failure cascades provides crucial training for contingency operations. by accurately modelling how spacecraft components respond to micrometeoroid impacts, system failures, or partial loss of capability. These simulations prepare operators to make effective decisions when things go wrong. This aspect of training has proven particularly valuable based on historical mission experiences, where creative responses to unexpected failures have often meant the difference between mission success and failure. Simulation fidelity continues to increase as computing power advances and more mission data becomes available. Each successful asteroid mission provides new information about the actual conditions encountered, allowing subsequent simulation systems to become more accurate. This creates a virtuous cycle where better simulations lead to more successful missions, which in turn enable even better simulations for future operations. Despite these advances, significant simulation limitations remain. No Earth-based system can fully replicate the combined effects of vacuum, radiation, microgravity, extreme temperatures, and psychological stress experienced during actual missions. Simulation designers must therefore focus on the most mission-critical aspects while acknowledging inherent uncertainties. This reality drives the conservative margins and redundant approaches that characterize spacecraft design and mission planning for asteroid environments. For future asteroid missions, simulation will likely incorporate even more aspects of actual mission operations, potentially including hardware testing in analog environments like the International Space Station or lunar facilities. These partial gravity, vacuum-exposed testbeds could provide intermediate validation between purely Earth-based simulation and actual asteroid operations. As commercial space capabilities expand, dedicated test platforms in Earth orbit might eventually offer opportunities to validate navigation systems in actual space conditions before committing to deep space missions. The steady improvement in asteroid navigation simulation capabilities represents one of the most important enabling factors for increasingly ambitious missions to these challenging environments. By allowing operators and systems to learn from virtual failures rather than catastrophic real ones, effective simulation makes possible the complex operations required to explore, study, dot, and potentially utilize the resources of our solar system's asteroid populations. While current simulation and training approaches continue advancing our capabilities within existing technological frameworks, a new generation of technologies promises to fundamentally transform asteroid navigation safety in the coming decades. These emerging innovations address the core challenges we've discussed throughout: detection limitations, maneuvering constraints, communication delays, and vulnerability to impacts, potentially opening new possibilities for safe operation in even the most hazardous asteroid environments. Advanced propulsion systems represent perhaps the most transformative technologies on the horizon. Current chemical rockets and ion thrusters force difficult trade-offs between thrust and efficiency that limit evasive capabilities. Several promising alternatives are in active development. Nuclear thermal propulsion, which uses a reactor to heat propellant rather than chemical combustion, could provide 2 to 3 times the efficiency of chemical rockets while maintaining high thrust capabilities. This combination would dramatically improve both emergency maneuvering capability and total mission delta V budget, allowing more frequent and aggressive evasive actions when needed. More exotic propulsion approaches show even greater long-term potential, and magnetoplasma dynamic thrusters can potentially achieve much higher exhaust velocities than current ion drives while providing greater thrust. Nuclear pulse propulsion, using small nuclear explosions for propulsion, remains controversial but offers theoretical performance far beyond any current technology. Fusion propulsion, while still largely theoretical, could eventually provide the ideal combination of high thrust and extremely high efficiency if the significant technical hurdles can be overcome. Revolutionary detection technologies promise to extend spacecraft awareness far beyond current capabilities. Quantum radar systems, currently in early development, could potentially detect smaller objects at much greater distances than conventional radar by exploiting quantum entanglement properties. Multispectral detection systems that simultaneously monitor across multiple wavelength bands, from ultraviolet through visible light into infrared and even terahertz regions, could identify objects regardless of their surface reflectivity properties, eliminating the current blind spots for very dark or very bright objects. Distributed sensor networks represent another promising direction for improving detection capabilities. Rather than relying on sensors aboard a single spacecraft, future missions might deploy constellations of small sensor platforms that collectively monitor a much larger volume of space. These distributed systems provide not just broader coverage, but multiple observation angles on the same objects, enabling more accurate trajectory determination and better discrimination between actual threats and false positives. Early versions of this approach are already being implemented in Earth orbit for space debris monitoring, with deep space applications likely to follow. Advanced materials science offers new possibilities for impact protection beyond current shield designs. Self-healing materials that can automatically repair small punctures are moving from laboratory curiosities toward practical applications. Gradient density materials that gradually change from very low density outer layers to high density inner protection can better absorb and distribute impact energy. Metamaterials with engineered properties at the microscopic level can potentially channel impact forces away from critical components through pathways designed into the material structure itself. Perhaps most revolutionary are active protection concepts that move beyond passive shielding. Electromagnetic shields that use magnetic or electric fields to deflect charged particles away from spacecraft remain largely theoretical but continue to advance through research programs. Plasma windows contained fields of charged particles might eventually provide adjustable, energy-based barriers against both radiation and physical impacts. While these technologies remain speculative for near-term missions, they represent the logical evolution of protection strategies as energy generation capabilities improve. Autonomous navigation capabilities continue advancing through artificial intelligence breakthroughs. Future systems will likely incorporate quantum computing elements that can solve the complex orbital dynamics problems of asteroid field navigation far more efficiently than classical computers. Neuromorphic computing architectures that more closely mimic human brain function show promise for the pattern recognition and intuitive decision-making that asteroid navigation requires. These advanced computing paradigms could eventually enable autonomous navigation capabilities that exceed human performance even in novel, unpredicted scenarios. Communication technologies are evolving to address the fundamental limits imposed by light speed delays. Optical communication using lasers instead of radio frequencies can dramatically increase data rates, allowing more comprehensive sensor information to be shared between spacecraft or transmitted back to Earth for analysis. Quantum communication, while still in early research phases, might eventually enable certain types of information sharing that bypass some limitations of classical communication, though it cannot overcome the fundamental light speed delay. For human missions, biomedical advances may help address some of the psychological and physiological limitations we've discussed. Pharmaceuticals that enhance attention and cognitive performance during critical navigation phases are under active research. Brain-computer interfaces might eventually provide more direct connections between human cognitive abilities and spacecraft systems, reducing the interface limitations of current control systems. Medical countermeasures against radiation exposure could reduce one of the major health risks associated with extended missions in asteroid environments. Swarm robotics approaches promise new strategies for both exploration and hazard mitigation. Instead of single, large spacecraft that represent catastrophic single points of failure, swarms of smaller vessels could collectively perform mission objectives while providing inherent redundancy. If some units are lost to impacts or failures, the overall mission continues with reduced capacity rather than ending completely. These distributed approaches align well with the unpredictable nature of asteroid environments, trading perfect efficiency for greatly enhanced robustness. Asteroid modification technologies, while controversial, could eventually provide options for making hazardous regions safer for navigation. Technologies being developed for planetary defense against potentially hazardous asteroids, including gravity tractors, kinetic impactors, or directed energy systems, could potentially be adapted to gradually reshape the orbital properties of asteroids in high-traffic regions, rather than navigating through hazards. Future missions might rearrange those hazards into more predictable, manageable configurations. Practical implementation of these advanced technologies will require not just technical development, but also new regulatory and operational frameworks. International cooperation on space traffic management will become increasingly important as more nations and commercial entities venture into asteroid regions. Standards for hazard notification, right-of-way protocols, and emergency response coordination will need to evolve alongside the technical capabilities that make expanded asteroid operations possible. While some of these technologies remain speculative or in early development stages, the history of space technology suggests that capabilities advance faster than often predicted when driven by clear mission requirements. As commercial interest in asteroid resources grows and scientific missions push deeper into these regions, the economic and scientific incentives for solving these navigation challenges will likely accelerate development across multiple technology fronts simultaneously. The combined effect of these emerging technologies promises to gradually transform asteroid field navigation from an exceptionally challenging high-risk endeavour into a more routine, manageable operation, while the physics of hypersonic impacts and the vastness of space ensure that asteroid environments will never be truly safe in an absolute sense. These technologies point toward a future where the remarkable resources and scientific knowledge contained in our solar system's asteroid populations become increasingly accessible to human exploration and utilization.